You picture a drop of blood moving silently through your veins. Carried within it are messengers too small to see, yet powerful enough to shape mood, growth, and survival. But how can a molecule so tiny decide when to comfort, when to stress, and when to age the body? Welcome to Rest Academy, where we calmly trace the science of your body as you rest. Tonight we'll map the entire endocrine system, how hormones whisper through the blood, how receptors translate signals into cascades, and how rhythms of light, stress, and time reshape them again and again. To make this journey complete, I've prepared a free practical guide with a concise summary of tonight's lesson, waiting in the description like a map you can return to whenever needed. Close your eyes, let curiosity turn to calm, and let's begin. Warm blood slides through elastic vessels while tiny parcels float within it. You picture those parcels as letters addressed to specific neighborhoods, a steady stream of messages that maintain pressure, temperature, growth, and fuel. The puzzle is simple to ask and subtle to solve. What counts as a hormone? What kinds exist? And how do they survive the trip to deliver meaning rather than noise? A hormone is a chemical messenger released into the bloodstream by specialized cells to influence distant targets that express matching receptors. The distance and the circulation matter. Many cells release local signals, but when the signal enters blood to reach remote tissues, you call it endocrine. Because targets may be far away and few receptors determine the response, the system values precision over brute force. Think of three broad envelopes for these letters. Peptide and protein hormones are chains of amino acids, folded, water-loving, and eager to dissolve in plasma. Steroid hormones are lipid-derived, built from cholesterol, and prefer fat to water. Amine hormones arise from single amino acids, chiefly tyrosine, split into two practical families, catecholamines like epinephrine and norepinephrine, and iodinated thyroid hormones, T3 and T4. This classification is more than a name. It predicts solubility, transport, receptor location, and timing. Solubility sets the postal route. Water-soluble peptides and catecholamines ride freely in plasma. They circulate unbound, meet surface receptors, and trigger fast, adjustable responses. Their free state confers short half-lives because enzymes in blood and tissues rapidly degrade them, and kidneys filter them out. Lipid-soluble steroids do not mix well with water. They bind to carrier proteins in plasma. Albumin provides broad carriage, while specialized globulins like corticosteroid-binding globulin and sex hormone-binding globulin improve stability and distribution. Bound hormone acts as a reservoir. Only the small free fraction can cross membranes and bind receptors. Thyroid hormones, although derived from an amino acid, behave more like steroids for transport. Iodination makes them hydrophobic, so they circulate largely bound to thyroid-binding globulin, transthyretin, and albumin, with a tiny free fraction mediating action. Half-life, the time needed for half the circulating hormone to be removed, follows these transport rules. Peptides and catecholamines live briefly, minutes, allowing minute-to-minute tuning. Steroids and thyroid hormones last longer, often many tens of minutes to hours, supporting sustained programs such as development, basal metabolic tone, or salt balance. Clearance arises from hepatic modification, cellular uptake, and renal excretion. Liver disease or nephrotic loss of binding proteins can therefore reshape free fractions and apparent potency without any change in gland secretion. Packaging and mailing differ as well. Peptide hormones are synthesized on ribosomes as preprohormones, trimmed in the endoplasmic reticulum and Golgi, and stored in secretory granules. A calcium-dependent exocytosis releases them in pulses when the cell is stimulated. Steroids are not stored. Cells synthesize them on demand from cholesterol via mitochondrial and smooth endoplasmic reticulum enzymes, and they diffuse out as soon as they form. Catecholamines sit in chromaffin granules ready for rapid release upon sympathetic stimulation, whereas thyroid hormone is uniquely prefabricated and stored extracellularly in colloid as iodinated thyroglobulin, then reclaimed and secreted when cues arrive. Because hormone concentrations are extraordinarily low, often in the picomolar to nanomolar range, messages rely on exquisite receptor affinity and specificity. That is why misfolded proteins, altered carriers, or receptor mutations can magnify or mute effects. It also explains why different tissues respond differently to the very same concentration, expression levels of receptors, availability of signaling partners, and local enzymes sculpt each response with neighborhood precision. The letter analogy grows. A free peptide is like a postcard speeding through open channels. A steroid bound to a carrier resembles a certified letter, traveling in a protective sleeve, released only at the right doorway. Thyroid hormones ride in padded envelopes that require a desk clerk, a membrane transporter to enter the building at all. The return address is your feedback system, which we will explore later. For now, the important point is that a correct address receptor, an accessible door transport, and a legible script signal encoding together determine meaningful delivery. A brief clinical vignette can ground this. Picture a middle-aged person with new generalized itching and yellowing of the eyes. Laboratory studies reveal elevated bilirubin and low levels of key binding proteins synthesized by the liver. Over several weeks, they note changes in menstrual regularity or libido without any change in pituitary output. Here, impaired hepatic protein production can lower the carriers for thyroid and sex steroids, transiently altering total hormone levels and free fractions. Such patterns deserve timely professional evaluation because systemic disease can masquerade as primary endocrine imbalance. You reflect, briefly, on how much work your body performs to keep signals clear. The bloodstream looks chaotic, but rules of chemistry make order possible. Shape, charge, and solubility decide the path long before a receptor ever sees a ligand. Your breathing stays slow as you hold one remaining question. When a hormone reaches its target, how does one touch on a membrane or in a nucleus translate into a coordinated cellular response that can ripple through tissues without drifting into noise? Picture a cell as a house surrounded by a high wall. A messenger knocks at the door. Sometimes the knock is enough to set off a chain reaction inside, and sometimes the messenger must walk through the gate and open a drawer directly. Why are there different ways of listening to the same bloodstream? Receptors are specialized proteins that detect hormones and translate their presence into a cellular change. You can divide them by location: membrane receptors on the surface, cytoplasmic receptors in the interior, and nuclear receptors bound directly to DNA. Each is matched to the hormone's chemical nature, ensuring that water-soluble signals act at the surface while lipid-soluble signals reach deeper. For peptides and catecholamines, the wall is impermeable. These hormones bind to membrane receptors, often G-protein-coupled receptors, GPCRs, or receptor tyrosine kinases, RTKs. A GPCR is like a switchboard. Once a hormone binds, the receptor changes shape and activates an intracellular G protein. This protein exchanges bound GDP for GTP and interacts with effectors such as adenylyl cyclase or phospholipase C. From there, second messengers like cyclic AMP, inositol triphosphate, IP3, or diacylglycerol DAG multiply the signal. These molecules spread rapidly, opening channels, releasing calcium, or activating protein kinases that phosphorylate multiple substrates. The key is amplification. One binding event creates a wave of effects. Receptor tyrosine kinases operate differently. They often dimerize two receptor units pair when a hormone binds. Their intracellular domains then phosphorylate each other, creating docking sites for signaling proteins. This mechanism underlies responses to growth factors and insulin, linking hormone binding to gene expression, metabolism, and cell division. Steroid hormones cross membranes without difficulty. Inside the cytoplasm, they meet receptor proteins that act as transcription factors. The hormone receptor complex translocates into the nucleus, binds specific DNA sequences, and alters transcription of target genes. This pathway is slower but more durable. Instead of shifting enzyme activity, it changes the proteins a cell produces over hours or days. Thyroid hormones add a twist. They require transporters to cross the membrane because of their iodinated structure, but once inside, they act through nuclear receptors already bound to DNA. Binding displaces repressors, recruits coactivators, and alters transcription. This hybrid strategy blends controlled entry with profound genomic influence. To see why this matters, imagine a person who drinks a liter of water before sleep and then awakens repeatedly. In some cases, this reflects a problem with antidiuretic hormone, ADH signaling. ADH is a peptide, It binds to GPCRs on kidney cells, raises camp, inserts aquaporin in water channels, and concentrates urine. If receptors or downstream messengers fail, water balance unravels. Persistent nighttime urination with fatigue or weight change deserves professional attention because it may signal systemic endocrine disease rather than just hydration habits. Reflecting on this, you notice how cells act like secure buildings. Some visitors hand instructions to the front desk, others walk straight to the archives, and a few change the blueprints themselves. The diversity of doors and locks is what lets one bloodstream serve all tissues at once. Still, one question remains. Once signals are transmitted, how do cells know when to stop? What prevents runaway cascades and allows hormones to wax and wane in natural rhythms? A pendulum swings, steady yet never still. Your body's hormones behave in a similar way, rising and falling with patterns that preserve stability. But how can a chemical message both maintain balance and allow bursts of change when needed? Feedback is the answer. Negative feedback dominates endocrine control. When a hormone reaches its effect, it suppresses the very signal that released it. Imagine heating a room. The thermostat detects warmth and turns off the heater once the target temperature is met. Likewise, rising thyroid hormone reduces thyroid-stimulating hormone TSH release, and rising cortisol dampens adrenocorticotropic hormone ACTH. This prevents excess and keeps levels within narrow ranges. Positive feedback is rarer but striking. In childbirth, uterine stretch stimulates oxytocin release. Oxytocin enhances contractions, which increase stretch, which further increases oxytocin. The cycle intensifies until delivery, when the stimulus disappears. Positive feedback is like a microphone placed too close to a speaker. The loop grows louder until an external stop occurs. Beyond loops, timing matters. Hormones rarely flow as a smooth line. They appear in pulses. Pulsatility protects receptors from desensitization and encodes information in rhythm. Gonadotropin-releasing hormone GnRH, for example, must arrive in pulses from the hypothalamus to drive normal reproductive function. A constant infusion would paradoxically silence the system. Rhythms stretch from minutes to days. Cortisol follows a circadian cycle, highest in early morning to prepare the body for wakefulness, then declining through the day. Growth hormone peaks in deep sleep, reinforcing repair and tissue building at night. These rhythms align with the suprachiasmatic nucleus of the hypothalamus, a master clock set by light-dark cycles. Disruptions to rhythm reveal the importance of timing. Jet lag demonstrates this. When light cues shift abruptly, cortisol and melatonin misalign with local day and night, producing fatigue and poor concentration. Endocrine cycles resynchronize slowly, at a pace of roughly 1 hour per day of time zone shift, leaving the traveler in temporary disharmony. Feedback also ensures cross-system cooperation. Calcium regulation illustrates this. Low serum calcium triggers parathyroid hormone, PTH, which releases calcium from bone, increases reabsorption in kidney, and boosts vitamin D activation to enhance intestinal absorption. When calcium rises, PTH secretion falls. Without this loop, small changes in diet or bone turnover would cause dangerous swings. A clinical picture grounds this. A patient complains of palpitations and heat intolerance. Testing reveals suppressed TSH alongside elevated free thyroxine. Here, the negative feedback is intact. TSH is low, but the thyroid gland itself is producing excess hormone autonomously. Recognizing this pattern prompts referral for professional assessment, since rhythm and feedback may signal deeper pathology when broken. You reflect briefly on the elegance. One bloodstream, yet different tissues send signals that restrain or reinforce each other. Stability emerges not from stillness, but from oscillations held in check. And still, a deeper puzzle forms. If loops and rhythms coordinate hormones, what central hub gathers the cues and broadcasts them across the body's glands? Deep within the brain, just above the palate, lies a crossroads where nerve signals meet vascular channels. Here, the hypothalamus and pituitary form a partnership that directs much of the endocrine orchestra. But how does a handful of neurons manage the pace of glands scattered across the body? The hypothalamus is a small region at the base of the brain, bordering the third ventricle. Its neurons secrete releasing and inhibiting factors into a specialized vascular system, the hypophyseal portal circulation, that flows directly to the anterior pituitary. This short vascular link allows micromolar pulses of peptides to exert powerful control without dilution in systemic blood. The anterior pituitary, also called the adenohypophysis, is glandular tissue that synthesizes trophic hormones. Each trophic hormone stimulates a peripheral endocrine gland. TSH activates the thyroid, ACTH the adrenal cortex, luteinizing hormone LH, and follicle-stimulating hormone FSH the gonads. Growth hormone GH influences liver and other tissues, while prolactin acts primarily on breast tissue. These pituitary signals magnify small hypothalamic cues into systemic endocrine cascades. The posterior pituitary, or neurohypophysis, works differently. It does not synthesize its main hormones, oxytocin and vasopressin antidiuretic hormone ADH, but stores and releases them from terminals of hypothalamic neurons. Electrical activity in the hypothalamus triggers exocytosis into systemic blood. This direct neural-to-blood pathway demonstrates that the hypothalamic pituitary unit is both gland and extension of the nervous system. Feedback loops bind the system together. For example, cortisol from the adrenal cortex suppresses both ACTH from the pituitary and corticotropin-releasing hormone CRH from the hypothalamus. Thyroid hormone similarly suppresses TSH and thyrotropin-releasing hormone TRH. Such dual-level feedback provides robustness, ensuring that errors at one node do not easily spiral. Anatomical connections add another layer. Neurons in the hypothalamus receive signals from higher brain centers, limbic, cortical, and brainstem inputs, so emotional state, stress, and sensory cues influence endocrine output. This explains why anxiety can alter menstrual cycles or why sleep deprivation disturbs growth hormone release. The endocrine system is not isolated chemistry, it is woven into perception and behavior. Consider a young adult with fatigue and darkening of skin folds. Laboratory data reveal low cortisol but high ACTH. The pituitary is working, but the adrenal cortex is not responding. This illustrates the trophic nature of ACTH. Chronic elevation stimulates melanocytes, darkening the skin. The clinical pattern shows how central signals and peripheral responses can be dissected to locate dysfunction. Professional evaluation is always required when central control seems disrupted, since symptoms can be subtle yet progressive. You may pause to picture the hypothalamus as a conductor raising a baton. Tiny flicks summon whole sections of an orchestra, yet the orchestra plays in time only because feedback tells the conductor when sound is too loud or too soft. A question still hovers: if the hypothalamus directs with such economy, what exactly are the notes played by the pituitary? How do its own hormones shape growth, reproduction, and water balance in detail? You notice how height, muscle tone, and even the shape of a child's jaw change gradually with age. These long arcs of growth depend heavily on one signal, growth hormone, or GH, released from the anterior pituitary. Yet GH rarely acts alone. It partners with insulin-like growth factor 1, IGF-1, secreted mainly by the liver. How do these two forces choreograph the body's expansion and repair? GH is a peptide hormone secreted in pulses, most prominently during deep slow-wave sleep. Its secretion is governed by two hypothalamic signals, growth hormone-releasing hormone GHRH, which stimulates, and somatostatin, which inhibits. The balance between them creates bursts of GH rather than constant release. Once in circulation, GH acts directly on some tissues, but more importantly induces IGF-1 production, which carries many of the growth-promoting effects. At the cellular level, GH binds to membrane receptors that dimerize and activate the JAK-STAT pathway, leading to transcription of growth-related genes. IGF-1, meanwhile, signals via receptor tyrosine kinases, engaging pathways that enhance protein synthesis, glucose uptake, and cell survival. Together, GH and IGF-1 stimulate bone elongation at growth plates, muscle protein accretion, and organ enlargement during childhood and adolescence. In adults, their actions shift toward tissue repair and metabolic balance. GH also affects metabolism directly. It reduces glucose uptake in peripheral tissues, increases lipolysis in adipose stores, and promotes hepatic gluconeogenesis. These actions provide fuel for growth but can raise blood glucose if unchecked. IGF-1 counters some of these effects by increasing insulin sensitivity, highlighting the intricate balance between them. Disturbances illustrate their power. Excess GH after growth plates close causes acromegaly, enlargement of hands, feet, and facial bones, along with metabolic disturbances. Before plates close, GH excess produces gigantism with extreme height. Deficiency conversely results in short stature in children and reduced muscle mass or energy in adults. Such conditions usually arise from pituitary tumors or genetic alterations, and recognition requires professional care. A red flag appears when someone develops progressive changes in facial features or shoe size. This deserves timely evaluation. A helpful image is a construction site. GH is the project manager issuing instructions: build here, repair there. IGF-1 is the crew that actually lays bricks, pours concrete, and wires the systems. Without GH, the crew never assembles. Without IGF-1, the manager's orders remain only words. Together they extend the scaffolding of the body, night after night, especially while you sleep. You reflect briefly. Growth is not only about size, but also about renewal. Even in adulthood, microtears in muscle after exertion are patched by this same system. The manager and the crew continue their quiet work long after the house is built. And yet questions linger. If GH and IGF-1 shape stature and metabolism, what other pituitary signals guide lactation, bonding, or water balance? Hormones whose effects are immediate and social as much as structural. Milk flows to a newborn's mouth, a uterus contracts at the final stage of labor, and kidneys quietly decide how much water to conserve. These scenes, different in setting, share a link to pituitary hormones beyond growth: prolactin, oxytocin, and antidiuretic hormone, ADH, each is small in size yet decisive in outcome. Prolactin is a peptide produced by the anterior pituitary. Its main role is to stimulate milk production in the mammary glands after childbirth. Unlike many pituitary hormones, prolactin does not act through a classical trophic axis. Instead, it is primarily under inhibitory control from dopamine produced in the hypothalamus. Removal of that inhibition allows prolactin to rise. Prolactin binds receptors that activate the JAK-STAT pathway, increasing transcription of milk proteins and enzymes necessary for sustained lactation. Oxytocin, stored in the posterior pituitary, is released in pulses triggered by sensory input. Stretch of the cervix during labor or suckling at the breast activates hypothalamic neurons whose axons end in the neurohypophysis. Release of oxytocin into the bloodstream drives uterine contractions and milk ejection by stimulating contraction of myoepithelial cells surrounding mammary alveoli. Beyond reproduction, oxytocin also influences social bonding and trust by acting on receptors in the brain, although these roles are still being mapped with caution. ADH, or vasopressin, also arises from hypothalamic neurons but acts primarily on the kidney. It binds V2 receptors on collecting duct cells, activating CAMP and protein kinase A. This cascade inserts aquaporin II water channels into the apical membrane, sharply increasing water reabsorption. The result is concentrated urine and preserved plasma volume. ADH release is exquisitely sensitive to plasma osmolality, rising with small increases in sodium concentration, but it also responds to blood pressure via baroreceptor input. Disruptions reveal the importance of these hormones. In diabetes insipidus, ADH is deficient or its receptor fails, leading to large volumes of dilute urine and persistent thirst. Conversely, excess ADH causes water retention and hyponatremia, producing confusion, seizures, or worse. With prolactin, inappropriate elevation can result from pituitary adenomas, leading to menstrual irregularities or infertility. A professional evaluation is warranted if someone notices unexpected lactation without pregnancy, persistent headaches, or visual changes. Think of these hormones as switches for flow. Prolactin primes the reservoir of milk, oxytocin opens the gates, and ADH manages the faucets of water inside your body. Though their tasks differ, all involve controlled release of fluids under tightly regulated triggers. Reflecting quietly, you see how subtle cues, a baby's touch, a drop in sodium, a neuron's pulse, become whole-body responses. The smallest drops change the largest tides. Still, another curiosity forms. If these signals govern fluids and nurturing, what controls the pace of energy, temperature, and alertness? The rhythms often traced back to the butterfly-shaped gland in the neck. A small gland shaped like a butterfly rests at the base of your neck, hugging the trachea. Though modest in size, the thyroid sets the pace of energy use for nearly every tissue. But how does this gland make its hormones, and why can the body falter when they rise too high or fall too low? Thyroid hormones are synthesized within spherical follicles lined by epithelial cells and filled with colloid. The process begins with iodide, an element absorbed from diet and actively transported into follicular cells. Iodide is oxidized and attached to tyrosine residues within a large protein, thyroglobulin, forming monoiotyrosine MIT and diotyrosine DIT. Two DIT molecules couple to form thyroxine T4, while one MIT and one DIT couple to form triiodopylene T3. These products remain stored in the colloid, bound to thyroglobulin, until stimulated. Thyroid-stimulating hormone TSH from the anterior pituitary triggers their release. Follicular cells endocytose colloid, proteolyze thyroglobulin, and liberate T4 and T3 into the circulation. In blood, they travel mostly bound to carrier proteins such as thyroxine-binding globulin (TBG), with only a tiny free fraction active at receptors. T4 is more abundant, but T3 is more potent. Much of circulating T4 is converted to T3 in peripheral tissues by deiodinase enzymes. At the cellular level, T3 enters nuclei through transporters and binds thyroid hormone receptors, which regulate gene transcription. Targets include genes controlling mitochondrial enzymes, Na plus K plus apase, and adrenergic receptor density. The result is increased basal metabolic rate, enhanced oxygen consumption, and heat production. Thyroid hormones also influence growth, brain development, and cardiovascular tone. When thyroid hormone falls below normal, the system slows. Hypothyroidism produces fatigue, weight gain, cold intolerance, bradycardia, and dry skin. In severe cases, swelling and slowed reflexes occur. Common causes include autoimmune destruction, Hashimoto disease, and iodine deficiency. Lab findings show high TSH with low free T4, reflecting intact negative feedback. When thyroid hormone rises excessively, the opposite occurs. Hyperthyroidism causes weight loss despite increased appetite, heat intolerance, tachycardia, tremor, and anxiety. A goiter often develops. Graves' disease, an autoimmune disorder where antibodies stimulate the TSH receptor, is a frequent cause. Laboratory studies reveal suppressed TSH with elevated free T4. If untreated, dangerous complications such as arrhythmias or thyroid storm can follow. A clinical scenario illustrates the balance. A person complains of persistent tiredness, coarse hair, and sensitivity to cold. Laboratory tests reveal elevated TSH and low T4. Professional evaluation is essential, as untreated hypothyroidism can progress insidiously. Recognition of the pattern, high TSH with low thyroid hormone, points to thyroid failure rather than pituitary disease. A simple metaphor helps. The thyroid is the thermostat of your body. When set too low, every system runs sluggishly, like a house chilled in winter. When set too high, the body overheats, wasting fuel and straining the machinery. You reflect briefly. One small gland calibrates the tempo of metabolism, proof that scale does not predict influence. Still, another puzzle emerges. If the thyroid governs energy, what keeps calcium, the body's most vital mineral, at safe levels for nerves, muscles, and bones? Imagine a violin string that must remain tuned within a narrow range. Too tight, and it snaps. Too loose, and it cannot play. Calcium in your blood behaves with the same precision, and three hormones, parathyroid hormone, PTH, vitamin D, and calcitonin, maintain its balance across bone, kidney, and intestine. PTH is secreted by the parathyroid glands, 4 small nodules usually embedded behind the thyroid. When plasma calcium falls, calcium-sensing receptors on parathyroid cells detect the change and trigger PTH release. PTH acts quickly on bone, stimulating osteoblasts to release signaling molecules that activate osteoclasts. Osteoclasts then resorb bone, liberating calcium and phosphate into circulation. In the kidney, PTH increases calcium reabsorption in distal tubules while decreasing phosphate reabsorption. preventing crystals from forming. Most crucially, PTH stimulates renal 1-alpha hydroxylase, converting inactive vitamin D into calcitriol, its active form. Calcitriol enhances intestinal absorption of calcium and phosphate by inducing calcium-binding proteins in enterocytes. This ensures that dietary calcium contributes effectively to balance. Unlike PTH, which acts minute by minute, vitamin D provides sustained support over hours to days. Together, they coordinate to restore calcium levels without prolonged deficit. Calcitonin, produced by parafollicular C cells of the thyroid, plays a counterbalancing role. When calcium rises, calcitonin suppresses osteoclast activity and promotes deposition of calcium into bone. Its effect is modest in adults but more pronounced in children and during pregnancy, when skeletal demands fluctuate rapidly. Consider what happens when this system falters. Hypocalcemia, low calcium, produces neuromuscular irritability. Symptoms can include tingling around the lips, carpopedal spasm, or seizures. Hypercalcemia, in contrast, depresses neuromuscular activity, causing weakness, constipation, kidney stones, and in severe cases, confusion. Both extremes require professional evaluation, as they may signal parathyroid disease, vitamin D disorders, or malignancy. Picture this system as a three-way negotiation. PTH argues to free calcium from storage, vitamin D secures outside supply, and calcitonin encourages saving excess in bone. The goal is never victory for one, but equilibrium for all. Reflect briefly. Your skeleton is not a static frame but a living bank, constantly lending and reclaiming minerals to serve momentary needs. Yet one question lingers. Beyond calcium, what other glands sit atop the kidneys, releasing hormones that determine survival and stress, salt balance, and adaptation to change? Just above each kidney rests a triangular cap, the adrenal gland. Its outer cortex manufactures steroid hormones, and its layered structure hints at multiple specializations. How does one small gland coordinate salt retention, stress response, and even contributions to sexual development? The adrenal cortex is divided into three zones. The outer zona glomerulosa produces mineralocorticoids, chiefly aldosterone. This hormone acts on distal nephron cells, stimulating sodium reabsorption and potassium secretion. By retaining sodium, water follows, stabilizing blood pressure and volume. Aldosterone secretion responds to the renin-angiotensin-aldosterone system and plasma potassium, with adrenocorticotropic hormone ACTH playing a supporting role. The middle zona fasciculata synthesizes glucocorticoids, primarily cortisol. Cortisol influences carbohydrate, protein, and fat metabolism. It promotes gluconeogenesis in the liver, mobilizes amino acids from muscle, and shifts fat distribution. Beyond metabolism, cortisol tempers immune responses and inflammation. Its release follows a circadian rhythm, highest in the morning, and surges during stress. ACTH from the pituitary is its main driver, itself controlled by hypothalamic corticoids and releasing hormone, CRH. The inner zona reticularis produces adrenal androgens, such as dehydroepiandrosterone DHEA. Though weaker than gonadal androgens, these hormones contribute to pubic and axillary hair growth in puberty and serve as precursors for sex steroid synthesis in peripheral tissues. In women, they form a meaningful source of androgens. In men, testicular testosterone predominates. When the cortex fails, Addison disease results. Cortisol and often aldosterone are deficient. Symptoms include fatigue, weight loss, low blood pressure, and skin hyperpigmentation due to elevated ACTH. In contrast, excess cortisol produces Cushing syndrome, marked by central obesity, muscle wasting, thin skin, and metabolic disturbances. Both conditions demand professional evaluation, as untreated adrenal insufficiency can be life-threatening, especially in stress. Think of the cortex as a three-story building. The ground floor secures salt and water, aldosterone. The middle floor manages stress and fuel, cortisol, and the top floor contributes auxiliary hormones for growth and sexual development, androgens. Together, they make the adrenal cortex essential for both daily survival and long-term adaptation. You reflect briefly, though hidden and small, the cortex balances basic life needs, pressure, energy, resilience, without conscious effort. But curiosity continues. If the cortex provides steady steroids over hours, what about the medulla at its core, where adrenaline surges in seconds to prepare the whole body for sudden change? At the heart of each adrenal gland lies the medulla, a cluster of chromaffin cells acting as modified sympathetic neurons. While the cortex releases hormones over hours, the medulla mobilizes the body in seconds. How can one organ provide both steady background support and emergency surges? The adrenal medulla secretes catecholamines, epinephrine, and norepinephrine derived from the amino acid tyrosine. Sympathetic preganglionic fibers release acetylcholine onto chromaffin cells, triggering exocytosis of catecholamine-filled vesicles. Once in circulation, these hormones amplify the fight-or-flight response beyond what local nerves alone could achieve. Epinephrine binds adrenergic receptors distributed throughout the body. In the heart, beta-1 receptors increase rate and contractility. In the lungs, beta-2 receptors relax smooth muscle to open airways. In the liver and muscle, both beta-1 alpha receptors mobilize glucose through glycogenolysis, while adipose tissue releases fatty acids for fuel. Blood vessels respond variably. Constriction in skin and viscera conserves blood for muscle and brain, while dilation in skeletal muscle ensures oxygen delivery. Norepinephrine, although similar, favors alpha receptors, producing stronger vasoconstriction and blood pressure elevation. The balance between epinephrine and norepinephrine depends on sympathetic tone and the specific stressor. Catecholamine action is brief because enzymes such as catecholomethyltransferase (COMT) and monoamine oxidase (MAO) degrade them rapidly. This brevity prevents prolonged crisis but requires rapid synthesis and release during repeated stress. Clinical patterns reveal dysfunction. Pheochromocytoma, a rare tumor of chromaffin cells, causes intermittent surges of catecholamines. Patients may present with episodes of severe headache, sweating, palpitations, and hypertension. Such patterns warrant medical attention, as undiagnosed surges can be dangerous. Visualize the medulla as the emergency siren of a city. At rest, it is silent, but when triggered, its alarm echoes everywhere: vessels, heart, lungs, liver. The alarm fades quickly once enzymes dismantle the signal, allowing return to calm. You reflect quietly. Survival depends not only on steady regulation, but also on bursts that prepare you for sudden demands. Balance means having both the calm hum of the cortex and the sharp call of the medulla. Yet another question arises. If catecholamines provide instant energy, how does the body maintain stable long-term fuel through insulin, glucagon, and the pancreatic islets? Energy must be available moment to moment, yet also stored safely for later use. The endocrine pancreas manages this balance through small clusters of cells called the islets of Langerhans. Within them, insulin and glucagon act as counterforces, shaping the ebb and flow of glucose. How do two hormones from the same organ decide whether fuel should be stored or released? Beta cells, the most abundant in the islets, secrete insulin. When you eat and glucose rises in blood, glucose enters beta cells via GLUT2 transporters. Intracellular metabolism raises ATP, which closes ATP-sensitive potassium channels. The resulting depolarization opens voltage-gated calcium channels, and calcium influx triggers exocytosis of insulin granules. Insulin then travels through blood, binding to receptor tyrosine kinases on target cells. Activation of the PI3K ACT pathway promotes insertion of GLUT4 transporters in muscle and adipose membranes, dramatically increasing glucose uptake. In the liver, insulin stimulates glycogen synthesis and suppresses glucose production. It also promotes fat storage and protein synthesis, making it a true anabolic hormone. Alpha cells secrete glucagon, which opposes insulin. When blood glucose falls, glucagon release rises. Glucagon binds G-protein-coupled receptors in hepatocytes, activating adenylate cyclase and CAMP production. Protein kinase A phosphorylates enzymes that drive glycogen breakdown and gluconeogenesis, releasing glucose into blood. Glucagon also mobilizes fatty acids from adipose tissue, ensuring fuel supply when carbohydrates are scarce. The two hormones form a yin-yang pair. Insulin dominates in the fed state, encouraging storage. Glucagon dominates in fasting, promoting release. Together, they keep plasma glucose within a narrow range, vital for neurons that rely almost entirely on glucose for energy. Dysregulation of this system underlies major disease. In type 1 diabetes mellitus, autoimmune destruction of beta cells leads to insulin deficiency. Without insulin, glucose remains in blood while cells starve, causing weight loss, thirst, and risk of ketoacidosis. In type 2 diabetes, insulin secretion persists, but tissues become resistant, requiring higher levels to maintain normal glucose. Over time, beta cells fatigue and complications arise in vessels, nerves, and kidneys. Both conditions demand professional management. Acute hypoglycemia illustrates the precision of balance. If insulin is excessive or meals are missed, glucose can fall too low. The brain responds with confusion, tremor, sweating, and in severe cases, seizures. Recognition and immediate correction are crucial, but the broader principle is clear. Tight regulation protects fragile neural function. Picture the pancreas as a marketplace. Insulin is the careful merchant storing goods in warehouses. Glucagon is the courier moving supplies into circulation when shelves run low. The two must coordinate, or else resources spoil unused or vanish too quickly. You reflect briefly. The steadiness of your mind, heartbeat, and breath depends on this invisible negotiation inside each meal and each fast. The simplicity of two hormones conceals an intricate, life-saving balance. Yet the story continues. If pancreas hormones safeguard fuel, what about the gonads, where endocrine signals shape puberty, reproduction, and the rhythms of sex hormones across life? In the quiet of evening, your body runs a calendar. Light fades, meals end, and a small circuit decides whether to invest in reproduction or hold back resources. That circuit, the hypothalamic pituitary gonadal axis, turns seasons of biology into pulses of hormone, shaping puberty, cycles, sperm production, and the textures of skin and hair. The axis begins with gonadotropin-releasing hormone GnRH, a dicapeptide from hypothalamic neurons. GnRH is released in pulses into the portal blood that feeds the anterior pituitary. Pulse frequency and amplitude carry information. Faster pulses favor luteinizing hormone LH release. Slower pulses favor follicle-stimulating hormone FSH. LH and FSH then travel through blood to the gonads, where they direct steroidogenesis and gametogenesis. Negative feedback closes the loop. Sex steroids and inhibins from the gonads restrain GnRH and gonadotropins, keeping output proportional to need. In ovaries, LH stimulates the Ka cells to convert cholesterol into androgens. FSH stimulates granulosa cells to aromatize those androgens into estradiol, the predominant estrogen before menopause. Rising estradiol during the follicular phase supports proliferation of the endometrium and increases FSH receptor expression on the dominant follicle. Most of the time, estradiol and progesterone inhibit GnRH and gonadotropins. However, sustained high estradiol near mid-cycle flips to positive feedback, triggering the LH surge that induces ovulation. After ovulation, the corpus luteum secretes progesterone, which stabilizes the endometrium and prepares it for implantation. When corpus luteum hormones fall, the endometrium sheds and a new cycle begins. In testes, LH stimulates Leydig cells to synthesize testosterone. FSH acts on Sertoli cells to support spermatogenesis, increase androgen-binding protein within seminiferous tubules, and secretin hymin B, which specifically feeds back on FSH. Temperature sensitivity, tubular architecture, and a blood testis barrier add local control so that systemic testosterone does not fully predict intratubular androgen action. Sex steroids act through nuclear receptors. Estradiol and progesterone bind receptors that regulate gene transcription, altering growth, vascular tone, and immune signals within reproductive tissues and beyond. Bone, brain, vessels. Testosterone binds the androgen receptor directly or is converted to two active derivatives, estradiol via aromatase, important in bone maturation and some brain regions, and dihydrotestosterone DHT via 5-alpha reductase, crucial for external genitalia development and some hair follicles. In blood, these steroids travel largely bound to sex hormone binding globulin SHBG and albumin, with a small free fraction driving receptor activation. Changes in SHBG shaped by liver function, Thyroid status and insulin levels alter free hormone availability without changing the measured total. Puberty is the axis's dramatic seasonal shift. Before it, the axis is quiet despite rising adrenal androgens, duranarchase that begin body odor and sparse hair. At puberty's onset, hypothalamic brakes loosen, kisspeptin neurons and other inputs awaken, and nocturnal GnRH pulses intensify. In girls, estradiol drives breast development, a growth spurt, and menarchase. In boys, testosterone enlarges testes and penis, deepens the voice, and fuels a later, taller growth spurt. Sex steroids potentiate growth hormone and IGF-1, accelerating linear growth and then closing epiphyseal plates to stop it. When tempo deviates markedly, very early sexual changes or absence of breast development or testicular enlargement by mid-adolescence, professional evaluation is important because the cause may be central, GnRH, pituitary, or peripheral gonadal. Polycystic ovary syndrome, PCOS, shows how metabolism and reproduction interlock. PCOS is a clinical syndrome marked by hyperandrogenism, hirsutism, acne, or biochemical evidence, ovulatory dysfunction, infrequent or absent ovulation leading to irregular cycles, and, in many but not all, polycystic ovarian morphology. Its physiology often features relatively rapid GnRH pulses that favor LH over FSH, increase the theca cell androgen output, and impaired granulosa aromatase activity. Insulin resistance is common. Higher insulin levels amplify the theca cell androgen production and reduce hepatic SHBG, raising free androgens. The endometrium may be exposed to unopposed estrogen if ovulation is infrequent, explaining heavy or unpredictable bleeding in some. Because PCOS also tracks with cardiometabolic risks over time, a pattern of irregular cycles plus signs of androgen excess merits professional assessment to differentiate PCOS from other androgen excess or adrenal conditions. Hypogonadism describes inadequate sex steroid action and impaired gametogenesis, and it divides into primary gonadal and secondary central forms. In primary hypogonadism, failing ovaries or testes produce low estradiol testosterone with high LH-FSH because the pituitary responds to low feedback but the gonads cannot answer. Causes include gonadal dysgenesis, autoimmune damage, infection, trauma, or toxic exposures, some chemotherapies, radiation. In secondary hypogonadism, the hypothalamus or pituitary fails to supply appropriate GnRH or gonadotropins. LH, FSH are low or inappropriately normal. Contributors include pituitary tumors, hyperprolactinemia, dopamine inhibition lifted, prolactin rises and suppresses GnRH, major systemic illness, stress or relative energy deficiency as in functional hypothalamic amenorrhea with undernutrition, high training load or both. In all forms, consequences extend beyond fertility, bone loss, changes in body composition, and mood or libido changes may follow. Concerning signals such as 3 months without menstrual bleeding unrelated to pregnancy, galactorrhea, hot flashes at an atypical age, new gynecomastia with testicular atrophy, or headaches with visual changes warrant timely professional care to determine the level of disruption and its cause. A short vignette grounds the logic. A 21-year-old long-distance runner reports 9 months of irregular or absent periods and increasing stress about fuel intake. Body mass index is low for her frame, and labs show low estradiol with low normal LH-FSH. The pattern suggests central suppression rather than ovarian failure. The seasonal clock has judged resources insufficient and has paused ovulation. The same mechanism can protect bone or fertility in the short term, but risks bone density loss if prolonged. Another reason this scenario deserves clinical attention. Hold the image of the axis as a greenhouse with timed lights. Green RH is the timer. LH and FSH are irrigation valves. Estradiol, progesterone, and testosterone are growth lamps that shift color across the day. When power is ample and timing precise, flowers open and seeds form. When power dwindles or the timer misfires, the greenhouse conserves instead of blooming. Across sexes, the same principles hold. Pulse-encoded central drive, trophic pituitary output, local steroidogenesis, and layered feedback. Differences lie in target anatomy and timing. The ovarian cycle alternates dominance between follicles and corpus luteum, whereas the testis maintains a relatively steady state of androgen production and spermatogenesis once mature. Both rely on adequate energy and sleep, and both crosstalk with thyroid and adrenal systems. You might reflect briefly on how sensitive this calendar is to context. Light, stress, illness, and nutrition can all reset the clock. When life demands change, biology renegotiates priorities so that survival outranks reproduction, and only when conditions improve does the greenhouse reopen. One soft line remains: your body listens for safety before it chooses growth. The next mystery is close. Which metabolic messengers tell the greenhouse how much fuel is in the soil? How do leptin and ghrelin signal abundance or scarcity? And how do thyroid hormones tune heat and thermogenesis, while body weight seems to defend its set point? The kitchen is dim and quiet, the hum of a refrigerator steady in the background. You feel a tug, not pain, not urgency, just a gentle pull toward food. Inside you, a conversation has already started. One voice reports how full the stores are, another argues for a refill, a third decides how much heat the system should produce. Energy balance is an accounting problem solved by biology. Expenditure has several ledgers: basal metabolic rate, energy to run essential cellular processes at rest; the thermic effect of food, costs of digestion and absorption; physical activity, planned exercise and non-exercise activity; thermogenesis neat, all the small movements that accumulate through a day. A final adjustable line item is adaptive thermogenesis, a flexible heater that rises with cold or excess intake and falls with scarcity. Hormones write numbers into each ledger, translating meals and seasons into metabolism. Leptin provides the main inventory report. Leptin is a peptide hormone produced by adipocytes, fat cells, in proportion to fat mass. When leptin reaches the hypothalamus, especially the arcuate nucleus, it binds receptors on two key neuronal populations. It stimulates pro-opiomelanocortin cocaine and amphetamine-regulated transcript POMC-CART-T neurons. These release alpha-melanocyte-stimulating hormone, alpha-MSH, that activates melanocortin-4 receptors MC4R downstream, reducing appetite and increasing energy expenditure. Leptin simultaneously inhibits neuropeptide Y-agouti-related peptide, NPY-AGERP neurons, that otherwise promote hunger and suppress energy use. The accounting message is clear: when stores are abundant, eat less and burn a bit more. But leptin's message is also about safety. Falling leptin seen with fasting, illness, or weight loss signals scarcity. The brain responds by increasing hunger, lowering thyroid drive slightly, and trimming neat. Reproductive and thyroid axes listen to this report. Low leptin dampens gonadotropin signaling and reduces thyrotropin-releasing hormone, TRH tone, a coordinated conservation strategy. In many forms of obesity, however, leptin levels are high, yet the expected satiety is blunted, a phenomenon often termed leptin resistance. Multiple mechanisms contribute: impaired transport across the blood-brain barrier, receptor-post-receptor signaling noise, and inflammation in hypothalamic circuits. So the inventory report arrives, but the accountant's voice is muffled. Ghrelin presents the other side of the ledger. Ghrelin is a stomach-derived peptide, secreted primarily by cells in the fundus, that rises before meals and falls afterward. It binds growth hormone, secretagogue receptors on NPY-AGRP neurons to increase hunger, and it also promotes growth hormone release from the pituitary useful when calories are scarce and the body must mobilize fuel. Ghrelin follows circadian and behavioral patterns. Short sleep tends to raise ghrelin and lower leptin the next day, biasing appetite upward and making highly palatable foods more attractive. In practical terms, your sleep schedule changes the tone of the appetite conversation long before willpower is even invited. Insulin participates as a quieter but persistent voice. After meals, insulin acts in the brain to support POMC activity and dampen NPY-AGRP signaling, aligning central satiety with peripheral storage. Nutrient sensors in hypothalamic neurons respond directly to glucose, fatty acids, and amino acids. Cellular pathways such as AMPK and mTOR integrate these cues with hormonal signals to set minute-by-minute tone. Vagal afferents from the gut carry information about distension and nutrient type, so the brain receives parallel messages: what you ate, how much, and how it fits into current reserves. Thyroid hormones translate those decisions into heat and work. Triiodothyronine T3 and thyroxine T4 increase basal metabolic rate by upregulating mitochondrial enzymes, stimulating AI plus K plus ATP, and reshaping lipid and carbohydrate handling. A special component of thyroid-dependent energy use is thermogenesis in brown and beige adipose tissue. Brown adipocytes are mitochondria-rich cells that express uncoupling protein 1, UCP1. UCP1 allows protons to leak across the inner mitochondrial membrane, uncoupling oxidation from ATP production and releasing energy as heat. Cold exposure activates sympathetic nerves that release norepinephrine, stimulating Ba3 adrenergic receptors on brown fat to raise UCP1 and burn fuel. Thyroid hormone amplifies this signal by increasing UCP1 expression and mitochondrial biogenesis. In effect, it makes the heater stronger and easier to switch on. Beige adipocytes are inducible cousins that arise within white fat depots under sympathetic and endocrine cues such as cold and certain hormones. They too can contribute to heat. Adaptive thermogenesis is where these systems meet. When energy intake falls below expenditure, leptin drops, ghrelin rises, and sympathetic and thyroid tones adjust to conserve. The result is a smaller total daily energy expenditure than size alone would predict. Basal processes slow slightly, NEAT unconsciously declines, and the heater turns down. This is not failure, it is defense. From an evolutionary perspective, the accounting system is designed to prevent starvation more vigorously than to prevent weight gain. Conversely, during overfeeding or cold exposure, sympathetic drive and thyroid-dependent thermogenesis rise, increasing futile cycles and heat production to limit excess storage and maintain temperature. Scientists debate whether body weight has a strict set point or a settling point, shaped by environment and behavior. Evidence suggests a defended range rather than a single number, with hormones like leptin, ghrelin, insulin, and thyroid hormones defining the range's edges. Within that band, cues such as sleep, stress, food environment, and activity nudge the balance. This explains why two people with similar diets may drift toward different stable weights, and why the same person can experience plateaus after weight change. The accountant has moved the thresholds, not to frustrate progress, but to preserve survival. A clinical vignette clarifies boundaries. A person reports unintentional weight loss over several weeks, persistent heat intolerance, palpitations, and new hand tremor. They also note increased appetite rather than loss of it. Such a pattern suggests that the heater is overactive relative to inventory, features compatible with thyroid overdrive. Because unintended weight loss with systemic symptoms can reflect endocrine or other medical disorders, this pattern deserves prompt professional evaluation to determine cause and appropriate next steps. Hold one image to tie these ideas together: an energy budget office. Leptin is the senior accountant reporting long-term assets. Ghrelin is the daily invoice that arrives before each meal. Insulin is the bookkeeper aligning deposits and withdrawals. Thyroid hormone sets utility rates for heat and maintenance. The sympathetic system dispatches space heaters, brown fat on cold days. When assets fall, the office cuts discretionary spending and postpones projects. When assets rise, it authorizes modest upgrades and allows a bit more warmth. You might reflect briefly that this office works whether or not you notice it. What feels like a single number on a scale is actually the emergent result of thousands of small entries in that ledger across brain, fat, muscle, liver, and gut. Your body protects you first. Goals come second. And a final question opens the next door. How does the stress system, the hypothalamic pituitary adrenal axis, reshape this budget by changing cortisol's rhythm across day and night? And why can travel or night shifts make hunger, heat, and wakefulness feel misaligned? Before dawn, the sky is a muted gray. Inside you, another morning begins, a quiet rise of cortisol that readies blood pressure, glucose availability, and alertness. This daily pattern is not an accident. It is the product of a timed stress system, the hypothalamic pituitary adrenal HPA axis, working with your master clock to align energy with the day ahead. How does that clock talk to stress circuits, and why does travel or shift work make hunger, heat, and wakefulness feel misaligned? The HPA axis is a three-step relay. Neurons in the paraventricular nucleus of the hypothalamus release corticotropin-releasing hormone, CRH, into the portal vessels feeding the anterior pituitary. In response, pituitary corticotropes secrete adrenocorticotropic hormone ACTH into systemic blood. ACTH reaches the adrenal cortex, especially the zona fasciculata, where it stimulates cortisol synthesis from cholesterol. Cortisol then circulates, largely bound to a carrier protein, with a small free fraction entering cells and binding glucocorticoid receptors that alter gene transcription. Negative feedback completes the loop. Cortisol restrains CRH and ACTH release, preventing runaway output. Timing overlays this relay. The suprachiasmatic nucleus, SCN, a small cluster of neurons above the optic chiasm, serves as the body's master circadian clock. Specialized retinal cells detect environmental light and send signals to the SCN. The SCN then adjusts downstream circuits, including the HPA axis, through multisynaptic pathways that reach the paraventricular nucleus and sympathetic nerves, projecting to the adrenal gland. The outcome is a daily cortisol rhythm, low levels during early sleep, a pre-awakening rise, and a peak shortly after you get out of bed. This early peak, often called the cortisol awakening response, adds a transient boost that helps you transition from sleep to activity. Cortisol is not just circadian, it is also pulsatile. Even within a day, secretion occurs in ultradian pulses that maintain receptor responsiveness and encode information in rhythm as well as amount. Pulses are more than decoration. Target tissues integrate both the size and timing of bursts, which helps explain why constant exposure to synthetic glucocorticoids can blunt receptors over time, while intermittent patterns may preserve sensitivity. What does cortisol do once it arrives? Think of it as a well-tuned dimmer rather than a simple on-off switch. In the liver, cortisol increases the capacity for gluconeogenesis, ensuring glucose can be supplied during fasting or challenge. In muscle, it mobilizes amino acids. In adipose tissue, it helps redistribute fat stores. In immune cells, cortisol tempers inflammatory gene programs, preventing overreaction. In the brain, it influences vigilance, memory consolidation for emotionally salient events, and mood, acting in conversation with the amygdala, threat appraisal, and hippocampus, context and memory. The same signal that prepares you to cope can, in excess or at the wrong time, disturb sleep, appetite, and affect. Sleep and the HPA axis interact bidirectionally. Entry into sleep, particularly slow-wave sleep early in the night, suppresses CRH and ACTH, helping keep cortisol low. In the second half of the night, as slow waves recede and rapid eye movement periods lengthen, CRH-ACTH tone rises, contributing to the pre-awakening cortisol climb. Disturbed sleep changes this choreography. Sleep restriction tends to elevate evening cortisol, flatten the daily slope, and amplify next-day hunger signals by raising ghrelin and lowering leptin. Over time, a flattened cortisol rhythm correlates with fatigue, impaired concentration, and metabolic strain. Acute stress overlays the daily pattern without erasing it. A sudden threat, pain, or intense emotion activates limbic inputs to the hypothalamus, increasing CRH and sympathetic outflow. ACTH spikes, the adrenals respond within minutes, and you are equipped to respond. Blood pressure rises, glucose becomes available, and non-essential processes pause. This surge is adaptive if brief. Chronic or repeated stress is different. Persistent drive can shift set points, alter hippocampal and prefrontal regulation of the axis, and contribute to a sense of being tired but wired. The concept of allostatic load, wear and tear from repeated adaptation, captures this idea. It is not one stressor, but the cumulative cost of many small adjustments that strains the system. Jet lag illustrates clock stress misalignment. Your SCN entrains primarily to light, peripheral clocks in liver, muscle, gut, and adipose tissue. Also listen to feeding and activity patterns. When you cross time zones quickly, the SCN shifts first, anchored to the new light-dark cycle, while peripheral clocks lag, still tuned to prior meal times and sleep windows. The HPA rhythm, partly paced by the SCN and partly by behavior, lands in between. For several days, cortisol peaks may occur at suboptimal local times, contributing to early waking, daytime sleepiness, and appetite drift. As behavior aligns with local light and meal times, peripheral clocks resynchronize, and the HPA rhythm settles back into a coherent slope. Shift work brings the problem home repeatedly. Night shifts require wakefulness during the biological night, and sleep during daylight, opposing the SCN's default. Cortisol secretion often becomes blunted in the morning after a night shift and elevated in the evening on days off, producing a pattern that satisfies neither schedule fully. The consequences extend across systems: impaired glucose tolerance on the circadian night, altered thyroid drive, and changes in leptin/ghrelin signaling that bias appetite toward quick energy. While individuals differ in resilience, persistent misalignment deserves attention because prolonged strain can masquerade as simple fatigue while affecting mood or blood pressure. A brief vignette grounds these mechanisms. A rotating shift nurse reports difficulty falling asleep on off days, new central weight gain despite unchanged meal size, and easy bruising. Examination notes proximal muscle weakness and a rounded facial contour developing over months. Here the story shifts from circadian misalignment to possible glucocorticoid excess. Such progressive features warrant professional evaluation because conditions that elevate cortisol chronically, whether adrenal, pituitary, or medication-related, can have serious systemic effects if unrecognized. One metaphor can hold the parts together. Imagine a house with a central clock and a thermostat linked to outside light. The clock SCN tells the furnace when dawn is near. The thermostat HPA axis raises the temperature a little so pipes do not freeze when you step into the morning air. Open a window in midwinter, an acute stress, and the thermostat boosts heat briefly. Move the house across time zones, and for days the clock chimes at the wrong hour while rooms warm at odd times. Only when curtains are opened and mealtimes move does the system find its new rhythm. You reflect briefly that your body protects function by predicting need. It warms you before you wake, tamps down inflammation before it smolders, and pauses some projects when the day grows unpredictable. Prediction, not reaction, is its quiet strength. A final question opens the next door. If clocks and the HPA axis govern daily readiness, what happens in pregnancy and lactation? When a temporary endocrine organ, the placenta, rewrites schedules, adjusts stress responses, and coordinates prolactin and oxytocin with fuel and fluid balance to nourish a new life, for 9 months your internal chemistry rewrites its own rules. A temporary organ, the placenta, joins your endocrine network, the pituitary enlarges, binding proteins rise, and multiple axes retune to sustain a fetus while keeping you upright, oxygenated, and stable. How do so many systems coordinate without stepping on each other's signals? Start with the placenta as an endocrine gland. The syncytiotrophoblast layer secretes human chorionic gonadotropin, HCG, a glycoprotein that resembles thyroid-stimulating hormone, TSH, and luteinizing hormone, LH, in structure. In early pregnancy, HCG rescues the ovarian corpus luteum, preserving progesterone production until the placenta itself makes enough steroid to maintain the uterine environment. By the late first trimester, placental steroidogenesis takes the lead. Cholesterol becomes progesterone, while estrogen synthesis uses precursors from the fetal adrenal, primarily dehydroepiandrosterone sulfate, that the placenta aromatizes into estradiol and estriol. This fetoplacental collaboration ensures that both maternal and fetal needs guide the steroid mix. Progesterone quiets uterine muscle. It reduces gap junctions among myometrial cells, dampens oxytocin receptor expression early on, and stabilizes the decidua. Estrogens, in contrast, promote growth of the uterus and breasts, increase uterine blood flow, and near-term help upregulate oxytocin receptors and gap junctions, so coordinated contractions can occur. A useful frame is tension and restraint. Estrogen prepares the stage, progesterone keeps the curtain down until late cues lift it. Human placental lactogen, HPL, also termed placental growth hormone variant, shifts maternal metabolism. HPL antagonizes insulin action in peripheral tissues, increasing maternal lipolysis and ensuring that glucose is spared for the fetus. As pregnancy progresses, insulin resistance rises. Pancreatic beta cells normally compensate by increasing insulin output. When compensation is insufficient, gestational diabetes can develop. Because both mother and fetus depend on steady fuel, persistent thirst, frequent urination, or unusual fatigue in pregnancy deserves professional evaluation to assess glucose handling and overall health. The HPA axis adapts too. Placental corticotropin-releasing hormone, CRH, increases across gestation and stimulates maternal ACTH and adrenal cortisol. Estrogen simultaneously raises corticosteroid-binding globulin, increasing total cortisol. Free cortisol also tends to rise. A placental enzyme, 11-beta-hydroxysteroid dehydrogenase type 2, converts active cortisol to inactive cortisone at the maternal-fetal interface, protecting the fetus from excessive glucocorticoid exposure. Late in pregnancy, the fetal adrenal enlarges, producing DHEA, that feeds placental estrogen synthesis. This loop helps time parturition. You can think of labor onset as a systems-level shift from progesterone-dominant restraint to estrogen/oxytocin prostaglandin permissiveness, with placental and fetal signals acting as the final conductors. The thyroid axis gains a distinctive twist. Estrogen raises thyroid-binding globulin, TBG, increasing total T4 and T3 in blood, while the free fractions remain near pre-pregnancy levels. Increased renal iodide clearance raises iodine needs for both mother and fetus. Early HCG can weakly stimulate the TSH receptor. As a result, TSH may dip in the first trimester, while total T4 rises within physiologic bounds. The operational rule is that binding proteins go up, totals go up, but free levels stay regulated. What matters to receptors are those free fractions. Volume and vasculature shift dramatically. Plasma volume expands, systemic vascular resistance falls, and the renin-angiotensin-aldosterone system is activated, increasing aldosterone to retain sodium and water. Red cell mass rises too, but less than plasma, producing the physiologic anemia of pregnancy by dilution. These coordinated changes deliver more blood to the uterus and placenta without overwhelming maternal pressure targets. Calcium and bone metabolism meet fetal demands through several levers. Intestinal calcium absorption increases, influenced by higher 1,25-dihydroxyvitamin D and estrogen. Parathyroid hormone-related protein, PTHRP, from placenta and breast contributes. In healthy pregnancies, maternal bone often remodels without significant long-term loss. Lactation alters the balance further, more below. Symptoms such as persistent muscle cramps, tingling around the mouth, or sudden weakness deserve clinical attention to evaluate minerals and endocrine contributors. The pituitary undergoes striking change. Lactotrophs, prolactin-secreting cells, hyperplasia under high estrogen, enlarging the gland. Prolactin rises to prepare for milk synthesis, but is functionally restrained by high estrogen and progesterone, which block milk secretion despite abundant machinery. At delivery, placental expulsion causes a rapid drop in estrogen and progesterone. The brake lifts and prolactin, driven higher by suckling-induced pulses, initiates milk production. Oxytocin, released in response to nipple stimulation, contracts myoepithelial cells around alveoli for milk ejection. This pairing, prolactin for milk synthesis, oxytocin for milk letdown, forms the lactation reflex. In the brain, oxytocin also tends to lower stress reactivity and foster caregiving behaviors. Still, its social effects, while compelling, remain nuanced and context-dependent. Lactation introduces a temporary adjustment to reproductive timing. Elevated prolactin suppresses hypothalamic GnRH pulses, reducing LH and FSH, and often delaying ovulation, a biologic spacing mechanism termed lactational amenorrhea. Its strength varies with feeding frequency and individual physiology. The concept is simple. Energy and attention prioritize the newborn, and endocrine circuits echo that logic by tempering rapid return to fertility. Two brief vignettes ground these ideas. First, a postpartum person experiences difficulty initiating breastfeeding, profound fatigue, lightheadedness, and failure to resume menses months after a complicated delivery with major bleeding. Here, concern shifts to possible pituitary injury from ischemia. Professional evaluation is important because interrupted pituitary signals can affect cortisol, thyroid, and lactation. Second, another postpartum person reports fluctuating anxiety, palpitations, then later fatigue and cold intolerance within the first year after delivery. That course may reflect transient autoimmune thyroiditis. Again, professional assessment clarifies the pattern and guides safe follow-up. A final thread is immune tolerance. Pregnancy requires acceptance of a semi-allogeneic fetus. Placenta-derived factors and shifts in maternal immune signaling promote tolerance without broadly weakening defense. After delivery, immune tone recalibrates. this change likely contributes to transient autoimmune phenomena in the postpartum window in some individuals. Hold one image to integrate the story. A temporary control tower docks to your body's airport. The tower placenta adds new radio channels, ACG, HPL, CRH, steroid signals, yet coordinates with existing towers, pituitary, thyroid, adrenals. Traffic increases, blood volume, binding proteins, metabolic flux, yet runways stay clear because each signal has timing and purpose. You reflect briefly that this is cooperative physiology at its most elegant: two organisms, one circulation, many safeguards, and reversible changes that more often than not reset smoothly after birth. And the next quiet question forms as evening returns. When reproduction recedes and decades pass, how do hormones reshape again? What patterns define menopause, testicular aging, and the slow drift of muscle and bone across the later years? Evening light softens on skin, joints feel the day's work, and muscles settle into a quieter tone. Inside, clocks that once drove growth and fertility now favor maintenance, repair, and economy. This gradual retuning is hormonal aging, a coordinated shift across reproductive axes, body composition, and the scaffolding that holds you steady. Menopause describes the permanent cessation of ovarian cycles after a sustained interval without menstruation. The mechanism centers on follicular depletion. Follicles provide estradiol and inhibin B. As their number declines, inhibin B falls first, reducing the brake on pituitary follicle-stimulating hormone FSH. Rising FSH cannot rescue exhausted follicles. Estradiol and progesterone production wavers, then drops. Without cyclical progesterone, the endometrium no longer prepares for potential implantation. The hypothalamic pituitary gonadal loop remains responsive, but the ovary's capacity to answer pulses is gone. The transition is not a single switch. Perimenopause spans years, marked by irregular cycles and variable hormone levels. Vasomotor symptoms, sudden heat with skin flushing and sweating, reflect altered thermoregulatory set points in the hypothalamus under changing estrogen tone. Sleep can fragment, especially with night sweats. Genitourinary tissues normally supported by estrogen become thinner and drier. The urinary tract may feel more irritable. Across bone, less estrogen increases osteoclast activity through signals such as Rankel from osteoblast lineage cells, tipping turnover toward resorption. The result is accelerated bone mineral loss in the first years after the final menstrual period. Over the long term, body fat tends to redistribute toward the abdomen, and low-density lipoprotein cholesterol may rise, reshaping cardiovascular risk patterns. Professional evaluation is appropriate when bleeding is unusually heavy or prolonged, when cycles stop unexpectedly at an atypical age, or when vasomotor or urogenital symptoms become disruptive to health or daily function. After cycles cease, estrogen from the ovary remains low, but it does not fall to zero. Peripheral tissues such as adipose express aromatase, converting adrenal androgens to weaker estrogens. This local synthesis contributes to tissue-specific effects. Progesterone, tightly tied to ovulation, falls more completely. FSH and luteinizing hormone LH remain high because feedback is minimal, a laboratory signature that helps distinguish ovarian senescence from central causes of amenorrhea. In men, change is slower and more heterogeneous. There is no abrupt counterpart to menopause. Testicular Leydig cell function gradually declines. Sex hormone binding globulin SHBG tends to rise, so free bioavailable testosterone decreases even when total values sit within population ranges. Spermatogenesis can diminish with age, yet many men sustain fertility. The term late-onset hypogonadism is sometimes used when symptoms, reduced morning erections, low libido, low energy align with consistently low testosterone concentrations, and other causes are excluded. Because many conditions, sleep apnea, obesity, systemic illness, medications, dampen the axis, persistent changes in sexual function or vitality should be discussed with a health professional to identify the level and cause, rather than assume aging alone. Both sexes experience adrenopause, a decline in adrenal androgens such as dehydroepiandrosterone DHEA and its sulfate. These weak androgens serve as substrates for peripheral conversion. Their fall may subtly influence skin, hair, and mood. Somatopause, the age-related decline in growth hormone and insulin-like growth factor 1, IGF-1, shifts protein balance and fat distribution. Thyroid physiology also drifts. While average thyroid-stimulating hormone TSH may creep upward with age in some populations, individual set points remain the best guide, reminding you that aging alters ranges but does not erase the need for context. Cortisol's daily slope may flatten slightly, and melatonin secretion typically diminishes, both contributing to lighter sleep and altered alerting signals. Sarcopenia names the progressive loss of skeletal muscle mass and function with age. It is not merely smaller muscles, it includes reduced strength and slower performance. Mechanisms intertwine, anabolic signaling wanes, lower IGF-1 and androgen tone, motor neurons are lost, and neuromuscular junctions remodel, mitochondrial function declines with more oxidative stress, and inflammatory mediators quietly rise, nudging protein turnover toward breakdown. Physical inactivity and insufficient protein intake accelerate these processes, while endocrine shifts, reduced estradiol, testosterone, and growth hormone, lower the ceiling for muscle protein synthesis. Muscle fibers themselves change, fast twitch units atrophy more than slow ones, and surviving motor neurons reinnervate abandoned fibers, creating larger but less efficient motor units. Consequences reach beyond strength. Muscle is a metabolic organ that clears glucose and secretes myokines that talk to bone, brain, and immune cells. With less muscle, insulin sensitivity falls, basal metabolic rate drops, and fall risk rises. Bone and muscle form a coupled unit. Osteocytes listen to muscle tension, and muscle contractions stimulate bone formation. When estrogen falls and muscle weakens, bone feels a double absence, more resorption with less mechanical stimulus to rebuild. The pairing explains why mobility, balance, and skeletal health tend to travel together in later life. Warning signs: unexplained weight loss, rapid decline in strength, new falls, or height loss merit professional assessment to look across endocrine, nutritional, neurologic, and medication contributors. A brief vignette draws the threads together. A 54-year-old notes irregular cycles for a year, hot episodes at night, and new midline back discomfort after lifting a light box. She also reports poorer sleep and less morning energy to exercise. Examination finds mild vertebral tenderness. Labs reveal high FSH with low estradiol. Here several transitions converge: perimenopausal estrogen variability, sleep disruption, and early musculoskeletal strain. Because fragility fractures can occur silently, and because cardiovascular and metabolic profiles shift in this window, timely clinical evaluation helps map risks and options without assuming every symptom is just menopause. Another scenario: a 67-year-old man reports dwindling morning vigor, reduced exercise tolerance, and gradual central weight gain. He snores loudly, occasionally nods off in the afternoon, and has a new diagnosis of elevated blood pressure. Before labeling this andropause, a careful review is needed. Sleep-disordered breathing, medications, thyroid function, and chronic disease can suppress testosterone and amplify fatigue. Professional guidance helps separate overlapping influences and choose safe, evidence-based steps. Hold one image to anchor the physiology. Your body is a suspension bridge spanning decades. Estrogen and testosterone are major load-bearing cables. GH, IGF-1, thyroid, and adrenal signals are the smaller cables and dampers. Muscle and bone are the deck and trusses that distribute force. With time, some cables thin, dampers loosen, and traffic patterns change. The bridge remains sound when inspections are regular, loads are anticipated, and components share strain rather than fail alone. You might reflect briefly that aging is not a single failure, but a recalibration. Slower pulses, altered thresholds, and a firmer prioritization of essential functions. The aim is continuity with fewer surges, more economy, and enough reserve to handle unexpected wind. One quiet question lingers as the night draws in. When physiology drifts and the thyroid's tempo slows or accelerates, how do medicines attempt to mimic nature's rhythm without overshooting? What principles guide thyroid pharmacology so the heater runs warm but not hot? A thermostat can drift, and so can the thyroid. When hormone output falters or overshoots, medicine steps in to restore balance. But how does therapy imitate a system designed to adjust in pulses, with carrier proteins and tissue-specific enzymes shaping effect? Understanding thyroid pharmacology means following the logic of replacement and inhibition rather than memorizing doses. Levothyroxine is the most widely used thyroid hormone preparation. It is a synthetic form of thyroxine T4, the main hormone secreted by the thyroid gland. In the body, T4 itself is less potent than triiodothyronine T3, but serves as a prohormone converted by deiodinase enzymes in tissues to active T3. By providing T4, replacement therapy relies on each tissue to generate the amount of T3 it needs. This mimics physiology, since most circulating T3 normally comes from peripheral conversion rather than direct thyroid secretion. Once absorbed, levothyroxine enters blood, where it binds to thyroxine-binding globulin, TBG, transthyretin, and albumin. Only a small free fraction is available to enter cells and bind nuclear thyroid receptors. Changes in binding protein concentration, therefore, shift total hormone levels without necessarily altering the free active fraction. Pregnancy, estrogen therapy, and certain liver conditions increase TBG, raising total T4 while free T4 remains stable. Recognizing this principle prevents misinterpretation of laboratory results. In contrast, liothyronine is synthetic T3. Its effect is more rapid and potent, but its half-life is shorter because it is less bound to carriers and more readily metabolized. This makes levels fluctuate, which can complicate steady replacement. Some combinations of T4 and T3 are used, but physiology favors T4 alone with peripheral conversion, except in select contexts where deiodination is impaired. Suppression therapy illustrates another principle. Because TSH stimulates thyroid growth, high doses of thyroid hormone can suppress TSH to reduce recurrence of certain thyroid cancers or manage nodular disease. Here the goal is not replacement but altering feedback. The risks of sustained TSH suppression, such as bone loss and arrhythmias, highlight the need for careful monitoring. When hormone excess rather than deficiency dominates, the strategy reverses: block synthesis, reduce release, or dampen peripheral action. Thyronamides, such as methimazole and propylthiouracil, PTU, inhibit thyroid peroxidase, the enzyme that oxidizes iodide and couples iodotyrosines on thyroglobulin. PTU also reduces peripheral conversion of T4 to T3. These drugs gradually lower hormone output because preformed stores in colloid must first be depleted. Side effects, though uncommon, range from rash to liver injury and agranulocytosis. Because of this, sudden fever or sore throat in someone taking thyronamides should prompt urgent professional evaluation. Iodine, normally a substrate for hormone synthesis, can at high concentrations paradoxically suppress release and organification, a phenomenon known as the Wolff-Chaikoff effect. Pharmacologic iodine, such as potassium iodide solutions, exploits this property to rapidly reduce hormone release in preparation for thyroid surgery or to blunt thyrotoxic crises. The effect is temporary, as the gland escapes with resumed hormone synthesis after several days. Radioiodine provides another strategy. Taken up by thyroid cells via the sodium iodide symporter, radioactive iodine emits BTI particles that damage and shrink thyroid tissue. This approach is used to treat hyperthyroidism and some thyroid cancers. Because it can reduce or abolish thyroid function permanently, monitoring and eventual replacement are often necessary. Beta-adrenergic blockers do not alter hormone levels but mitigate symptoms. In hyperthyroidism, excess thyroid hormones increase beta-adrenergic receptor density and sensitivity, amplifying palpitations, tremor, and anxiety. Blocking these receptors calms the cardiovascular system while definitive therapy takes effect. Imagine the thyroid system as a furnace. Replacement therapy supplies fuel logs, levothyroxine, that burn steadily, allowing each room tissue to draw the heat T3 it needs. Thionamides partially close the flue, reducing the rate logs are burned. High-dose iodine briefly damps the flame, like closing an air vent. Radioiodine removes bricks from the furnace altogether, shrinking its size. Beta blockers do not touch the fire itself, but quiet the rattling radiators, making the house more comfortable until the fire stabilizes. Consider a vignette. A person experiences unintentional weight loss, restlessness, and palpitations. Tests confirm hyperthyroidism, and methimazole is started. 2 weeks later, they develop sudden fever and sore throat. This scenario raises concern for agranulocytosis, a rare but serious side effect, and requires immediate medical attention. The story illustrates how understanding mechanisms guides vigilance. If a drug suppresses bone marrow, infection risk is the key clue. You reflect briefly. Medications cannot mimic every nuance of thyroid rhythm, but they follow principles: replacement where hormone is absent, inhibition where it is excessive, and support where symptoms outrun the underlying fix. And the next question stirs. If thyroid pharmacology balances temperature and pace, how do medicines for glucose aim to steady energy without exhausting insulin or leaving tissues unfed? After a meal, the room feels warmer, eyes relax, and your thoughts come a little easier. Quietly, molecules of glucose slip from gut to blood, and an old conversation resumes: store or spend. In pharmacology, you influence that conversation with agents that guide insulin, curb glucose production, slow absorption, or spill sugar through the kidney. The aim is not brute force but orchestration, matching pathways to physiology so fuel reaches cells without flooding the stream. Insulin is the body's prime anabolic signal for glucose. It binds a receptor tyrosine kinase on target cells, triggering PI3K-ACT signaling that moves GLUT4 transporters to muscle and adipose membranes, increases glycogen synthesis, and quiets hepatic glucose output. Pharmacologic insulin attempts to imitate natural patterns, a steady background presence to restrain hepatic output and discrete peaks to cover meals. Chemically modified insulins alter absorption and duration by changing self-association or binding properties, allowing a spectrum from rapid to prolonged action. Regardless of formulation, the central risk is hypoglycemia, a state where supply to the brain dips too low for function. Shakiness, confusion, or unusual behavior are warning patterns that deserve timely professional evaluation. Insulin may also favor weight gain because it promotes storage. This reflects biology's design to prevent waste, not a flaw in intention. Metformin sits upstream of insulin by shaping production rather than pushing uptake. It is a biguanide that reduces hepatic gluconeogenesis, the liver's glucose output, through effects that include mild inhibition of mitochondrial complex I and activation of AMP-activated protein kinase, AMPK. AMPK acts as a fuel gauge, shifting cells toward catabolism and improved insulin sensitivity. Metformin also alters the gut. It increases glucose utilization by enterocytes, changes bile acid signaling, and can raise endogenous GLP-1 levels. Because it does not drive insulin secretion, metformin rarely causes hypoglycemia by itself, and it tends to be weight neutral or modestly weight reducing. Gastrointestinal discomfort is its most common limitation. Persistent or severe symptoms should be discussed with a clinician to weigh benefits and tolerability and to screen for conditions that alter risk. Incretin-based therapies capitalize on a physiologic reflex. Oral nutrients amplify insulin secretion more than intravenous glucose because gut hormones prime pancreatic islets. Glucagon-like peptide 1, GLP-1 receptor agonists mimic this gut signal. They enhance glucose-dependent insulin secretion, suppress inappropriately elevated glucagon after meals, slow gastric emptying, and act in the brain to reduce appetite. Glucose-dependent is the safety feature. When glucose is low, stimulation fades, so hypoglycemia risk is low unless combined with agents that push insulin irrespective of glucose. Many people experience early satiety and gradual weight reduction. Gastrointestinal effects, nausea, fullness are common at the start and often subside with time. Rare but concerning patterns such as severe, persistent abdominal pain or vomiting merit prompt care to evaluate for uncommon complications. A related class, dipeptidyl peptidase 4 DPP4 inhibitors, prevents breakdown of endogenous incretins. Their effect on glucose is more modest. They are generally weight neutral and they rely on intact islet responsiveness. Sodium glucose cotransporter 2, SGLT2 inhibitors, redirect glucose handling to the kidney. In the proximal tubule, SGLT2 normally reclaims most filtered glucose back into blood. Blocking it allows glucose to be excreted in urine, lowering plasma levels independent of insulin. The result is a gentler glucose curve, small caloric loss, mild osmotic diuresis, and often a slight drop in blood pressure. Beyond glycemia, hemodynamic and cellular effects in the heart and kidney have translated into clinical benefits for many people with and without diabetes. Their predictable trade-offs flow from mechanism, More glucose in urine can foster genital yeast infections, volume depletion can occur in those already on diuretics, and in rare instances, ketoacidosis can develop even when glucose is not markedly elevated, especially in settings of low insulin availability or acute illness. Unexplained nausea, abdominal pain, and malaise with normal or moderately elevated glucose is a pattern that warrants urgent professional assessment in anyone using these drugs. Secretagogues drive the pancreas directly. Sulfonylureas and the shorter-acting meglutinides close ATP-sensitive potassium channels in beta cells, depolarizing the membrane and triggering insulin release regardless of ambient glucose. Their strengths are potency and simplicity. Their liabilities are hypoglycemia and weight gain. Most likely when meals are delayed, intake is reduced, or kidney function declines. Because the trigger is distal to the glucose sensing step, the system cannot easily let go when sugar falls, a key reason vigilance and individualized selection matter. Insulin sensitizers reframe how tissues respond. Thiazolidine-diones activate peroxisome proliferator, activated receptor gamma PPAR gene, a nuclear receptor that remodels adipocyte biology. By promoting storage in subcutaneous fat and improving adipokine profiles, they increase insulin sensitivity in muscle and liver. The benefits emerge slowly over weeks as gene expression changes. Their trade-offs include fluid retention, weight gain that disproportionately reflects water and subcutaneous fat, and a tendency to worsen edema or heart failure in susceptible individuals. A separate concern is reduced bone density in some. New fractures or swelling are signals to seek evaluation. Agents that act in the gut change the rate of supply rather than the demand for disposal. Alpha-glucosidase inhibitors slow the enzymatic breakdown of complex carbohydrates in the small intestine, blunting post-meal glucose spikes. Gas and bloating are unsurprising side effects because undigested carbs reach the colon. An amylin analog, pramlintide, complements insulin in some contexts by slowing gastric emptying and suppressing postprandial glucagon. It modestly reduces meal excursions, but, like insulin, can predispose to hypoglycemia if coordination is poor. Choosing among these classes is less about a single best drug and more about matching mechanism to biology and context. You align levers with needs. Reduce hepatic output when nocturnal glucose rises, improve insulin signaling when resistance dominates, blunt peaks after meals by slowing entry from the gut, spill sugar in urine when assistance independent of insulin is helpful, temper appetite and restore incretin tone when satiety is out of tune. Comorbidities, kidney and liver function, and cardiovascular or renal goals guide emphasis. Technology, continuous glucose monitoring, connected pens and pumps adds timing and feedback, turning pharmacology into a more responsive system without replacing the need for clinical judgment. 2 brief vignettes clarify boundaries. A person on a sulfonylurea skips lunch during a busy shift and later feels sweaty, shaky, and confused. Here the medication pulled insulin without sugar to match. Another person on an SGLT2 inhibitor develops sudden nausea and abdominal discomfort after a viral illness while eating very little. Their glucose meter shows only moderate elevation. This pattern is concerning for ketoacidosis despite near normal glucose and warrants urgent assessment. These are not instructions, they illustrate how mechanism predicts what matters. Hold a single image to integrate the field. Imagine a city's energy grid. Insulin opens loading docks so fuel enters factories. Metformin asks the power plant to output less at night. GLP-1 messages slow incoming trucks and tune workers' appetite for raw material. SGLT2 opens relief valves at the reservoir. Secretagogues ring the bell that summons extra loaders. Thiazolidine-diones reorganize warehouses so delivery routes shorten. When the grid is coordinated, lights stay steady with less waste. You might reflect briefly that the body's priority is continuity. Pharmacology works best when it partners with that priority. Small nudges at multiple checkpoints rather than one overwhelming shove. A final question turns the page. When you borrow the body's own steroids to reduce inflammation or sustain blood pressure, how do those medicines reshape feedback, thin the signals of the HPA axis, and what quiet risks appear when the borrowed voice becomes too loud for too long? When you borrow a voice to quiet inflammation, the body listens, and then if the voice stays too long, your own whisper fades. That is the paradox of therapeutic steroids, powerful relief paired with the possibility of silencing the hypothalamic pituitary adrenal HPA axis that normally sets cortisol's rhythm. Understanding this system helps you see benefits and risks as two sides of the same mechanism. Glucocorticoids are steroid hormones that act primarily through the glucocorticoid receptor GR, a ligand-activated transcription factor present in many cells. In the absence of hormone, GR waits in the cytoplasm complexed with chaperone proteins. When a glucocorticoid enters the cell, endogenous cortisol, or an exogenous drug, it binds GR, the complex travels to the nucleus, and it influences gene transcription by docking at glucocorticoid response elements or modulating other transcription factors. The genomic effects explain both anti-inflammatory benefits and metabolic consequences. Faster, non-genomic actions also occur via membrane-associated GR and interactions with signaling cascades, accounting for some rapid hemodynamic or immune changes observed after administration. Anti-inflammatory actions are broad. Glucocorticoids repress genes that drive cytokine production, such as interleukins and tumor necrosis factor pathways, reduce adhesion molecules on endothelial cells, stabilize lysosomal membranes, and decrease eicosanoid synthesis by upregulating annexin A1 and downregulating cyclooxygenase 2. In immune cells, they promote apoptosis of certain T-cell subsets and eosinophils while impairing antigen presentation. Clinically, this translates to reduced swelling, pain, and tissue damage across many conditions characterized by immune overactivity. Yet the same signals reshape metabolism. Glucocorticoids increase hepatic gluconeogenic capacity, mobilize amino acids from muscle, and shift fat distribution, favoring central depots over peripheral. They also reduce osteoblast function and prolong osteoclast survival, tipping bone turnover toward loss. In skin, they slow collagen synthesis, thinning dermis and weakening wound repair. In the eye, they can impede aqueous humor outflow, raising intraocular pressure in susceptible individuals. In the brain, they may alter mood, sleep, and attention. Some people describe a brief lift, others anxiety or irritability. Mineralocorticoids, principally aldosterone, act through the mineralocorticoid receptor, MR. MR resides in epithelial cells of the distal nephron and collecting duct, where activation increases sodium reabsorption and potassium secretion, raising extracellular volume. MR also exists in non-epithelial sites, heart, vessels, brain, where signaling intersects with fibrosis and blood pressure regulation. Under normal physiology, cortisol circulates at far higher concentrations than aldosterone, but is locally inactivated to cortisone in MR-expressing epithelia by the enzyme 11-beta-hydroxysteroid dehydrogenase type 2, 11-beta-HSD2, protecting MR from cortisol's sway. Inhibition or saturation of 11-beta-HSD2 removes this shield, allowing cortisol to activate MR and mimic mineralocorticoid excess. Two enzymes therefore shape steroid action. 11-beta-HSD2, cortisol, cortisone, guards MR-rich tissues, and 11-beta-HSD1, cortisone or cortisol, amplifies glucocorticoid tone in liver and adipose. Their balance helps explain tissue-specific effects and why some synthetic glucocorticoids with different affinities for GR-MR yield distinct profiles. For example, more or less sodium-retaining activity. Carrier proteins add another layer. Corticosteroid-binding globulin, CBG, and albumin keep most hormone bound. Only free hormone enters cells. Conditions that change CBG concentrations alter measured totals without necessarily changing free levels, an interpretive nuance that matters when reading labs. Exogenous glucocorticoids come in many routes: systemic, oral, intravenous, local but partly systemic, inhaled, intra-articular, epidural, transdermal, ocular, and topical to skin or mucosa. Local delivery aims to concentrate benefit and minimize systemic exposure, yet absorption still occurs. Duration and dose are not the only determinants of risk. Potency, route, hepatic metabolism, and concurrent illness all shape exposure. Mineralocorticoid therapy conceptually replaces aldosterone-like action when it is deficient or modulates MR tone in specific disorders. Its effects predictably include sodium retention and potassium loss, with blood pressure changes that merit monitoring. The HPA axis fuels exogenous steroids as if cortisol were high. Through negative feedback, hypothalamic corticotropin-releasing hormone, CRH, and pituitary adrenocorticotropic hormone, ACTH, decrease. The adrenal cortex quiets. With continued exposure, adrenal zona fasciculata cells atrophy, reducing intrinsic cortisol production. If exogenous supply stops abruptly after sustained use, the atrophic gland cannot immediately meet physiologic needs, especially under stress, risking adrenal insufficiency. Symptoms can be vague: fatigue, dizziness, nausea, or acute hypotension, severe weakness. Because these patterns overlap with common illnesses, and because stress raises normal cortisol demand, anyone with a history suggesting sustained exogenous steroid exposure who develops concerning symptoms warrants prompt professional evaluation. Risks mirror mechanisms. Immune modulation increases susceptibility to certain infections or blunts. Typical signs: reactivation of latent infections is a known concern. Bone mineral density may decline, particularly with prolonged systemic use. Vertebral compression fractures can occur with minor loads. Muscle can weaken. Steroid myopathy, typically in proximal groups. Skin may bruise easily and wounds may heal slowly. Striae can form where skin stretches over time. Eyes may develop cataracts or increased intraocular pressure, especially with prolonged exposure. Metabolic effects include hyperglycemia and, over time, altered fat distribution. Neuropsychiatric effects can range from insomnia and restlessness to mood changes. Rare cases involve more severe disturbances. Mineralocorticoid activity, whether from aldosterone, cortisol acting unopposed at MR, or a drug with MR effect, raises sodium and water retention potential, contributing to edema or hypertension and lowering potassium. 2 vignettes illustrate range and subtlety. First, someone uses high-potency topical steroids under an occlusive dressing for weeks to calm a stubborn rash. The skin improves, but they develop easy bruising, facial rounding, and new fatigue. Despite topical use, systemic features emerge. Potent agents on thin skin, large surface areas, or under occlusion can suppress the axis. Second, a person with long-term inhaled steroids for airway disease notices gradual proximal muscle weakness and more frequent upper respiratory infections. Inhaled routes reduce but do not eliminate systemic exposure, especially at higher potencies or with certain devices. Technique, formulation, and total exposure matter. In both cases, professional assessment helps connect the pattern to cumulative steroid effect and plan safe adjustments. Conceptually, tapering exists to let the axis wake without shock, but the specifics depend on duration, dose, route, and clinical context. The principle is simple: allow hypothalamus and pituitary to resume CRH and ACTH pulses while the adrenal cortex rebuilds capacity. During periods of physiologic stress, infection, surgery, trauma, requirements for endogenous cortisol rise. If the axis remains suppressed, the system may need temporary support. The educational takeaway is not a regimen, but a map: feedback, atrophy, recovery, and the special demands of stress. Interactions with other systems are common. Thyroid status alters steroid protein binding. Liver disease changes metabolism and CPG. Diabetes interacts through glucose handling. Bone health through turnover. Cardiovascular status through volume and pressure. Vaccination timing and infection surveillance are clinical considerations because immune responses can be blunted. Because these domains interlock, patterns such as recurrent infections, new edema, vision changes, sudden mood shifts, or postural dizziness while on or after steroid therapy warrant timely evaluation rather than assumption. Hold one metaphor to keep the mechanism straight. Exogenous steroids are a borrowed public address system. At first, the amplified message quiets crowd noise, inflammation, so work can proceed. If the microphone stays on, your own voice, CRH, ACTH, cortisol, grows silent, the room rearranges to the amplified tone, metabolism, bone, skin, and the speakers begin shaping the acoustics themselves. MR effects on pressure and potassium. Turning the system down gradually allows natural voices to return without chaos, but only if the room has time to readapt. You might reflect briefly that the potency you borrow is never free. Physiology keeps ledgers. Relief remains real and often necessary, and prudence lives in recognizing early signs when the balance tips. A question awaits at the threshold. If benefits and risks hinge on mechanisms and feedback, how do clinicians read the ledgers? What patterns in screening tests and dynamic suppression or stimulation studies reveal whether a gland is overactive, underactive, or simply responding to another's whisper? The room is quiet, except for the soft hum of a centrifuge. A small label bears your name, and inside the tube signals circulate: TSH, cortisol, sodium, waiting to be read. Endocrine testing is less about numbers than about asking the right question first: screening, function, or mapping. Begin with a principle. Screening tests estimate whether an axis is likely normal at rest. Dynamic tests challenge an axis to reveal reserve or autonomy. Imaging maps anatomy only after chemistry tells you which organ is missignaling. Think of labs as gauges on a dashboard, and dynamic tests as controlled stress on the system. Only when the gauges prove a problem do you open the hood with imaging. Thyroid function illustrates the logic. Thyroid-stimulating hormone, TSH, serves as a sensitive sentinel for primary disorders because the pituitary magnifies small changes in free thyroxine. In primary hypothyroidism, TSH rises while FT4 falls. In primary hyperthyroidism, TSH is suppressed while FT4 and often free triiodothyronine, FT3, are high. When TSH is low yet FT4 is not elevated, subclinical hyperthyroidism is a possibility. Conversely, high TSH with normal FT4 suggests subclinical hypothyroidism. If TSH is low or inappropriately normal with low FT4, suspicion shifts to central pituitary or hypothalamic disease, where TSH loses its reliability as a single guide and FT4 anchors interpretation. Binding proteins complicate totals. Pregnancy and estrogen therapy raise thyroxine binding globulin, inflating total T4 while the free fraction remains steady. Non-thyroidal illness can flatten results, lowering T3 first. Biotin supplements can artifactually distort immunoassays. Timing and assay selection matter. Antibody tests, anti-thyroid peroxidase, anti-TSH receptor answer why, not how much, and may confirm autoimmune mechanisms or receptor stimulation. When the question is structure, ultrasound surveys nodules and parenchyma. When the question is function in thyrotoxicosis, radionuclide uptake distinguishes Graves' diffuse uptake from thyroiditis, low uptake, or toxic nodules focal uptake. Imaging follows, not precedes, the biochemical story. Adrenal diagnostics split into deficiency and excess. For suspected cortisol deficiency, an early morning serum cortisol provides a first look. Because the circadian peak occurs near waking, very low values raise concern, while mid-range results are ambiguous. Dynamic evaluation asks the gland to respond. A standardized ACTH, cosintropin stimulation test, probes adrenal capacity to raise cortisol. If the question is pituitary reserve rather than adrenal readiness, other physiological challenges exist conceptually, but safety and clinical context govern their use. For cortisol excess, screening aims to detect loss of normal suppression and timing. An overnight low-dose dexamethasone test checks whether exogenous glucocorticoid feedback can lower morning cortisol. Late-night salivary cortisol asks if the diurnal nadir is preserved. 24-hour urinary-free cortisol estimates integrated exposure. One positive screen can be misleading. Stress, depression, alcohol, and certain drugs raise noise, so confirmation by a second independent test is common. Only once biochemistry confirms hypercortisolism do you measure ACTH to direct imaging. Low ACTH suggests an adrenal source and leads to adrenal imaging. Normal or high ACTH suggests a pituitary or ectopic source and points to pituitary MRI or specialized localization. The order matters because incidental adrenal and pituitary nodules are common. Imaging first invites false leads. Carrier proteins, corticosteroid-binding globulin, and exogenous steroids complicate interpretation. Free indices and medication review maintain clarity. Water balance rests on osmolality. Serum sodium and serum osmolality tell you about the extracellular compartment. Urine osmolality reveals renal response. When thirst is relentless and urine abundant yet dilute, the differential includes diabetes insipidus, central, nephrogenic, and primary polydipsia. A controlled dehydration challenge followed by desmopressin conceptually asks two questions: can you concentrate urine, and will a vasopressin signal help? Euvolemic hyponatremia with inappropriately concentrated urine raises suspicion for syndrome of inappropriate antidiuretic hormone. The lab triad, low sodium, low serum osmolality, high urine osmolality, plus clinical context supports the pattern. Confusion, seizures, or severe nausea and hyponatremia are danger signals that warrant urgent professional care because the brain is exquisitely sensitive to rapid osmotic shifts. Calcium testing begins with the specimen itself. Total serum calcium must be interpreted with albumin, or ionized calcium can be measured directly when precision is critical. Intact parathyroid hormone, PTH, tells you whether the parathyroid axis is driving the change or responding to it. Primary hyperparathyroidism features elevated or inappropriately normal PTH with high calcium. Malignancy-related hypercalcemia commonly suppresses PTH while other markers rise. Vitamin D status relies on 25-hydroxyvitamin D for stores, not 1,25-dihydroxyvitamin D, which varies with PTH and kidney function. Low urine calcium in the setting of mild hypercalcemia and normal or high PTH suggests a familial set point shift rather than glandular overactivity. Parathyroid imaging, ultrasound, or sestamibie-based localization does not diagnose, it guides a surgeon once biochemistry has done the diagnosing. Tingling lips, muscle cramps, or sudden weakness with calcium derangement should prompt evaluation. Extremes can be unsafe. Glucose evaluation answers different questions. Fasting plasma glucose and glycated hemoglobin A1C reflect baseline states. An oral glucose tolerance test, OGTT, challenges beta cells and peripheral tissues with a defined glucose load, revealing impaired tolerance or diabetes by the trajectory of the curve. In pregnancy, modified OGTT protocols screen for gestational diabetes because placental hormones drive insulin resistance. Here the stake is dual maternal and fetal fuel. A1C can mislead when red cell turnover is altered. Fasting and OGTT remain the reference for those contexts. For suspected hypoglycemia, you seek Whipple's triad conceptually. Low measured glucose, symptoms consistent with neuroglycopenia, and relief when glucose is restored. The physiology behind the event, excess insulin, limited counter-regulation, or exogenous factors, requires careful supervised evaluation. Growth hormone assessment depends on what not to do. A random GH level rarely helps because secretion is pulsatile. For excess, insulin-like growth factor 1, IGF-1, provides a stable screen. Failure of GH to suppress during an OGTT supports acromegaly physiology. For deficiency, stimulation tests ask the pituitary to produce GH under controlled stress. Selection depends on safety and context, and is not interchangeable with a resting level. Prolactin is straightforward, yet full of nuance. Mild elevations can arise from stress, sleep, or medications that reduce dopamine tone. Persistent marked elevations call for repeating under standardized conditions. Very high true prolactin can artifactually read lower in some assays hook effect, which improves with dilution. Another artifact is macroprolactin, a large complex that elevates measured prolactin but has less bioactivity. Laboratories can distinguish it. Only after excluding physiologic and drug causes does pituitary imaging answer where. Headache with visual field changes plus hyperprolactinemia is a pattern that merits prompt evaluation. Catecholamine secreting tumors require biochemical proof before scans. Plasma-free metanephrines or 24-hour urinary fractionated metanephrines detect the continuous footprint of catecholamine metabolism better than a spot catecholamine level. Stress, certain drugs, and positioning can skew results. Standardized collection reduces noise. If the footprint is present, cross-sectional imaging follows. Functional imaging is reserved for specific scenarios. Paroxysmal severe headaches, palpitations, and sweats with marked blood pressure surges are concerning symptoms that should be discussed promptly with a professional. One more rule ties the laboratory to the scanner: pre-test probability. The likelier a condition is based on history and exam, the more a test result, positive or negative, changes your view. When likelihood is low, incidental imaging findings in borderline labs mislead. When likelihood is high, a negative single test may need confirmation. Endocrinology rewards patience, precise questions, stage challenges, and imaging only when the chemistry has spoken. Hold a single image, a wind tunnel for physiology. You measure the airplane at rest screen, then run controlled gusts to see which surfaces flex, stimulate, or suppress, and only then do you lift the skin of the fuselage image to fix what you already know is off. You reflect briefly that the calm confidence of a clear sequence question, gauge stress map, prevents hurried detours. But sometimes the wind is no longer controlled. If the dashboard blares alarms, acid breath and deep breathing, fever with raging tachycardia, collapse with vomiting, then you face emergencies, not calibration. Next, you will walk through the patterns that signal diabetic ketoacidosis, thyroid storm, and adrenal crisis before they spiral. Monitors chirp, a fan hums, someone's breathing grows deep and regular, then faster, as if the body is trying to blow off something invisible. Another person is flushed and restless, eyes bright, heart racing. A third lies pale and clammy, pressure falling despite fluids. These patterns look different yet share one fact. When endocrine control fails abruptly, the whole system feels it. Endocrine emergencies are network failures. They are not subtle drift but collapse of a control room that normally coordinates glucose, heat, and pressure. 3 stand out for speed and danger: diabetic ketoacidosis, thyroid storm, and adrenal crisis. Each reflects a core mechanism gone to an extreme. Each can be recognized by a characteristic pattern, and each requires urgent professional care because multiple organ systems shift at once. Start with diabetic ketoacidosis, DKA, a state of insulin deficiency with counter-regulatory hormones in overdrive. Without insulin, glucose cannot enter key tissues efficiently. The liver interprets this as starvation despite plenty of sugar in blood. Glucagon, cortisol, catecholamines, and growth hormone rise, pushing hepatic gluconeogenesis and glycogen breakdown. Adipose tissue, no longer restrained, releases free fatty acids. The liver converts these into ketone bodies, beta-hydroxybutyrate and acetoacetate, that provide fuel to the brain and muscle during true famine, but acidify blood when produced unchecked. Meanwhile, high glucose drags water and electrolytes into urine, osmotic diuresis, dehydrating the body and washing out sodium and potassium. Serum potassium may be normal or high at first, shifted out of cells by acidosis and lack of insulin, even as total body potassium is low. Clinical features follow directly from chemistry. Deep, rapid air hunger breathing, a compensatory pattern to lower carbon dioxide, and a characteristic fruity odor on the breath reflect the acid load and volatile ketone species. Nausea, vomiting, and diffuse abdominal pain are common. People feel very thirsty, yet produce large volumes of urine until volume collapses. Confusion can appear as dehydration and acidosis worsen. Lab patterns include hyperglycemia and anion gap metabolic acidosis, elevated serum or urine ketones. Beta-hydroxybutyrate is the dominant species, low bicarbonate, and variable sodium, often apparently low because water shifts with glucose. Triggers include new-onset autoimmune diabetes, missed or interrupted insulin, infection, myocardial infarction, and pancreatitis. In children and adolescents, the risk of cerebral edema during treatment is a special concern. In adults, overlapping hyperosmolar states complicate the picture when ketones are lower but osmolarity runs very high. Any combination of rapid breathing, severe thirst with frequent urination, abdominal pain, and altered thinking in a person with diabetes or with symptoms suggestive of undiagnosed diabetes warrants immediate medical evaluation. Thyroid storm sits at the other end of the energy spectrum, a surge of thyroid hormone action combined with exaggerated tissue responsiveness. Thyroid hormones increase transcription of proteins that raise basal metabolic rate and sensitize tissues to catecholamines by upregulating beta-adrenergic receptors. In storm, excessive hormone effects and heightened adrenergic tone drive hyperthermia, tachyarrhythmias, including atrial fibrillation, high-output heart failure, agitation or delirium, and gastrointestinal hepatic dysfunction, vomiting, diarrhea, jaundice. The skin is hot and moist. The mind may race from anxiety to confusion. Diagnosis is primarily clinical because free hormone levels do not distinguish severe thyrotoxicosis from storm with enough speed. What marks storm is decompensation across systems. Precipitants include infection, trauma, childbirth, surgery, abrupt cessation of antithyroid drugs and iodine loads, contrast media, certain medications. Amiodarone presents a special case. It contains iodine and alters deiodinase activity, so both hormone synthesis and conversion can be perturbed. The conceptual picture is of a boiler that not only overheats but also seizes the building's ventilation controls, heart, brain, gut at once. Red flags include very high fever, a new rapid irregular heartbeat, shortness of breath out of proportion to exertion, confusion, and severe gastrointestinal symptoms in someone known or suspected to be thyrotoxic. This constellation signals an emergency requiring expert care. Adrenal crisis is the collapse of cortisol and often aldosterone. When the body most needs them, cortisol normally supports vascular tone, maintains glucose supply in stress, and tempers inflammation. Aldosterone, when deficient in primary adrenal failure, sustains sodium reabsorption and potassium excretion. In crisis, the stress system cannot rise to meet demand. The result is profound weakness, nausea and vomiting, abdominal pain that may mimic other acute conditions, hypotension that responds poorly to fluids alone, and often fever. In primary adrenal insufficiency, damage to the adrenal cortex itself, hyperpigmentation may have preceded the crisis due to chronically high ACTH, salt craving, and orthostatic symptoms are common clues. Labs can show hyponatremia, hyperkalemia with primary failure, hypoglycemia, and sometimes eosinophilia. In central adrenal insufficiency, pituitary or hypothalamic, hyperkalemia is absent because aldosterone remains relatively intact. Triggers include infection, injury, surgery, dehydration, and abrupt interruption of chronic glucocorticoid therapy. The essential insight is simple. When external or internal stress rises, cortisol requirements rise. If endogenous production cannot increase and exogenous support is missing, the system decompensates quickly. Any scenario of shock with abdominal pain, vomiting, and known adrenal insufficiency, or a history of chronic glucocorticoid use demands urgent professional attention. A single control room metaphor ties these states together. In DKA, the fuel valve sticks off at the cell surface, insulin absent, so the control room mistakenly orders emergency generators, ketones, and drains the water tower, dehydration, to keep lights on. In thyroid storm, the furnace is jammed high, and the fans run wild, overheating circuits everywhere. In adrenal crisis, the master stabilizer is absent. Breakers trip with minor surges because the system has no buffer. Same room, different failures, each recognizable by its sound and smell if you know where to listen. Brief vignettes illustrate pattern recognition. A teenager with 2 weeks of thirst and weight loss arrives with vomiting and deep breathing. The meter shows very high glucose and the air carries a sweet solvent-like scent. Think DKA and act urgently. A postpartum adult with untreated hyperthyroidism develops a soaring fever, agitation, and an irregular pounding heart after an infection. Storm until proven otherwise. A traveler with autoimmune Addison disease develops vomiting and diarrhea and cannot keep usual medication down. They grow dizzy and confused with darkening skin creases. This is crisis physiology, not simple dehydration, and needs immediate care. You reflect for a moment on the body's logic. Each emergency is an amplified version of a normal program. Ketosis in fasting, thermogenic drive in wakefulness, cortisol surge at dawn, pushed past safety bounds. Calm recognition comes from understanding the program before it fails. One line remains: emergencies teach the shapes of failure, stories cement them in memory. In the final part, you will walk through integrated cases, hyperthyroidism and flux, decompensated diabetes and adrenal failure, and then let the system wind down gently together. A student reviews notes late at night, recalling how each gland works in isolation. But real life does not arrive as single mechanisms. It arrives as people layered with symptoms that blur boundaries. Cases bring the system alive, not puzzles to solve here, but stories to see how patterns intertwine and why recognition matters. Begin with hyperthyroidism. A 32-year-old arrives with weight loss despite large meals, constant restlessness, and a heart that races even at rest. Examination shows tremor, warm moist skin, and mild eye prominence. Labs reveal suppressed TSH with elevated free T4. The triad symptoms, suppressed pituitary signal, high thyroid hormone, marks true hyperthyroidism. The differential includes Graves' disease, toxic multinodular goiter, and thyroiditis. Antibodies or uptake studies, ordered after biochemistry, refine the cause. Recognition matters because unchecked hyperthyroidism stresses the heart and bone and may progress to thyroid storm under physiologic stress. In the narrative of this person, the thyroid is not just overactive, it is teaching you to link labs and physiology, to hear pace too high in every finding. Now, decompensated diabetes. A 45-year-old presents with polyuria, polydipsia, abdominal pain, and confusion. Breath smells faintly fruity, and deep rapid breathing fills the room. Labs confirm hyperglycemia, low bicarbonate, high anion gap, and elevated beta-hydroxybutyrate. This is diabetic ketoacidosis, the physiology of fuel mismanagement, insulin absent, glucagon unchecked, ketones high, volume depleted. Triggers include infection or missed insulin. Recognition is urgent because without insulin's restraint, every counter-regulatory hormone pushes harder and the spiral accelerates. The teaching is not about numbers, but about the body's mistake. Plenty of fuel in blood, but none in cells. Seeing the mismatch in symptoms, thirst, urination, acid breathing, anchors the diagnosis before labs confirm it. Finally, Addison disease decompensating. A 28-year-old reports chronic fatigue, salt craving, and progressive skin darkening. Suddenly, after gastroenteritis, they collapse with abdominal pain, vomiting, and hypotension. Sodium is low, potassium high, glucose modestly reduced. Here, the adrenal cortex can no longer mount cortisol or aldosterone responses. Pituitary ACTH has been high for months, stimulating melanocyte receptors and darkening skin. The crisis unfolds because infection increases demand, but supply is absent. The key lesson is context. Known autoimmune disease, chronic fatigue with hyperpigmentation, and collapse after stress together form a pattern that experience will not forget. Professional evaluation and immediate support are vital in such scenarios. These vignettes condense months or years of physiology into a single event. They are not instructions but reminders. Endocrine failure rarely hides, it speaks in combinations. Tremor plus tachycardia plus weight loss, thirst plus acid breath plus confusion, fatigue plus hyperpigmentation plus collapse. Cases train your mind to link distant findings into one system. Hold an image as the series closes, a tapestry woven from fine threads. Each hormone is a thread, small, fragile, easily overlooked, yet together they build a fabric strong enough to regulate energy, growth, stress, reproduction, and sleep. When one thread frays, the pattern shifts. When many align, the fabric holds. You reflect briefly beneath skin and bone. Dialogue is constant, self-correcting, and often unnoticed. What you have traced is not a set of glands but an orchestra. Hypothalamus keeping time, pituitary sending cues, thyroid and adrenals carrying melody, gonads and pancreas adding harmony. The music is steady, yet capable of crescendos or sudden silences. And now the score rests. The system you have walked through, hormones and their organs, returns to quiet equilibrium, waiting for the next day's light to begin another cycle. As you settle into the end of this long exploration, the tempo softens. Each gland has spoken in turn, the thyroid whispering pace, the pancreas balancing fuel, the adrenals guiding stress and salt, the gonads shaping growth and reproduction. Together they form an interwoven system, not isolated parts. You may notice the body's theme is not command but conversation. Hormones rarely act alone. They travel, bind, adjust, and withdraw, all within loops that favor stability. Even emergencies, when they appear, are exaggerated versions of normal responses, not alien intrusions. The safety of physiology lies in its predictability once the logic is clear. Now, as the story closes, you can let the many mechanisms drift into background hum. Feedback loops, pulses, receptors, and pathways return to quiet operation. The body you inhabit is never still, but it is steady, and most of the time it protects balance without asking for notice. Allow that thought to settle. Beneath the noise of each day, there is an ongoing rhythm of regulation, continuous and calm. The endocrine system, complex, elegant, and often unseen, keeps the world inside you in tune with the world outside.